Most people grow up believing that humanity's fate is inseparable from the sun. It is the great constant in our lives, rising every morning with such dependable rhythm that it feels almost outside the reach of time itself. Even when we learn that stars are born and eventually die, the event seems so unimaginably distant that it belongs more to abstract astronomy than to our own future. The common assumption is simple. When the sun dies, humanity dies with it. Modern astronomy paints a more complicated picture. The sun is not merely a source of light. It is an evolving star whose slow transformation has already begun changing by amounts too small for any human lifetime to notice. At the same time, our own species has become increasingly capable of leaving the world that first gave us life. One process unfolds through the laws of stellar physics, the other through curiosity engineering and the gradual expansion of civilization beyond Earth. Together they create an unexpected paradox. The sun will almost certainly become uninhabitable for Earth long before it truly dies, yet humanity may not need Earth in order to survive. If that possibility is real, another question quietly emerges. What does it actually mean for civilization to outlive its own star? Is survival simply a matter of finding another planet? Or would every step farther from the sun transform humanity into something fundamentally different from the people who once watched sunrise over ancient oceans? Over the course of this journey, we will follow the evidence across billions of years through the life cycle of stars, the evolution of planets, the discovery of distant worlds, and the remarkable possibilities suggested by modern astronomy. Each answer will reveal another question, carrying us farther from familiar skies and closer to one of the deepest mysteries our species can ask. When the final daylight arrives for the sun, will it truly mark the end of humanity? Or only the end of the first chapter of our cosmic story? There is something reassuring about the sun's consistency. Every culture in human history has built its understanding of time around its steady presence. Days begin with its light. Seasons follow its changing path across the sky. Crops grow because of its warmth. Oceans circulate because of its energy. Even the air we breathe is part of a chain of events powered almost entirely by sunlight. It is so deeply woven into everyday existence that it can be difficult to think of the sun as anything other than permanent. Astronomy asks us to look at that familiar object in a very different way. The sun is not an eternal flame suspended in the heavens. It is a star, one among hundreds of billions scattered throughout the Milky Way. It appears unique only because it is close. If we could somehow drift far beyond the outer planets and look back toward our solar system from several light years away, the sun would lose its overwhelming brilliance. It would become just another bright point among countless others nearly impossible to distinguish from its stellar neighbors. That simple change in perspective was one of humanity's greatest scientific revolutions. For thousands of years, the stars seemed fundamentally different from the sun. One ruled the day while the others decorated the night. Only gradually did astronomers realize that they all belonged to the same family. The sun is simply the nearest example of something the universe produces in astonishing numbers. Yet being ordinary does not make it unimportant. The sun contains more than 99.8% of all the mass in the solar system. Every planet, moon, asteroid, and comet together account for only a tiny fraction of what orbits around it. Its gravity binds the entire planetary system into a stable structure. Without that immense gravitational anchor, Earth would not trace its nearly circular path through space. It would wander into the darkness between the stars. Its gravity provides the architecture. Its light provides the energy. Together they make life possible. Deep inside the sun, nearly 700 million tons of hydrogen are transformed every second into helium through nuclear fusion. The numbers are almost impossible to picture. Every second, a small fraction of that mass is converted directly into energy according to the relationship described by Einstein's famous equation E equals mc squared. The result is a continuous outpouring of light heat, and radiation that has remained remarkably stable for billions of years. The photons produced in the sun's core do not immediately escape into space. Instead, they begin an extraordinarily long journey. A photon created near the center is constantly absorbed and re-emitted by surrounding particles, changing direction millions upon millions of times. Although light crosses the distance from the sun to Earth in only about 8 minutes once it reaches the surface, a photon may spend tens of thousands and possibly hundreds of thousands of years working its way outward through the dense interior before finally escaping into space. The sunlight warming your face today may therefore represent energy that began its journey long before the first cities were built, before agriculture spread across continents, perhaps even before our own species developed civilization. That slow movement of energy hints at something larger. Stars operate on timescales completely unlike our own. Human history stretches back a few thousand years in written form. Recorded astronomy reaches only a few millennia further. Even the oldest human artifacts occupy only a tiny fraction of Earth's history. The sun, meanwhile, has been shining steadily for approximately 4.6 billion years. If we compress the sun's lifetime into a single calendar year, all of recorded human history would occupy only the final few seconds before midnight on December 31st. From the sun's perspective, civilizations appear and disappear almost instantly. This enormous difference in timescale explains why the sun seems so constant. Not because it never changes, but because it changes so slowly that multiple human civilizations can rise and fall without noticing any significant difference in its brightness. Yet astronomers know something that our ancestors could never have suspected. The sun is not frozen in time. Every second its core composition changes ever so slightly. Hydrogen is gradually depleted. Helium slowly accumulates. The balance between gravity pulling inward and nuclear fusion pushing outward continually adjusts itself. The changes are extraordinarily gentle, but they are real, measurable and irreversible. In many ways, the sun resembles a living system, not in the biological sense, but as a dynamic object constantly evolving while maintaining outward stability. It breathes through cycles of magnetic activity. Dark sunspots appear and disappear across its surface. Towering arcs of plasma rise thousands of kilometers into space before collapsing again. Powerful eruptions occasionally send streams of charged particles racing across the solar system, producing brilliant auroras on Earth, while reminding us that our seemingly peaceful star possesses tremendous power. Despite these storms, the sun belongs to what astronomers call the main sequence, the long and stable phase during which stars spend most of their lives converting hydrogen into helium. This stage is not unusual. In fact, it is the longest and calmest chapter in a star's existence. Stars much larger than the sun burn through their fuel rapidly, living only millions of years before ending in spectacular supernova explosions. Smaller stars consume their hydrogen much more slowly. Tiny red dwarfs can remain stable for trillions of years, far longer than the current age of the universe itself. The sun occupies a comfortable middle ground. It is massive enough to sustain abundant energy, but modest enough to enjoy a lifespan measured in billions rather than millions of years. That fortunate balance made Earth possible. Life had enough time to emerge from simple chemistry, survive planetary catastrophes, evolve increasing complexity, and eventually produce beings capable of asking where sunlight comes from in the first place. This perspective changes the way we think about habitability. Earth is not merely located at the right distance from the sun, it also exists at the right moment in the sun's lifetime. Had the sun been significantly brighter billions of years ago, Earth's oceans might never have remained liquid long enough for life to begin. Had it evolved much faster, complex organisms might never have appeared before conditions deteriorated. Our civilization exists during an unusually favourable interval. Not at the beginning of the sun's story, not near its end, somewhere in the long quiet middle. And yet even this peaceful chapter cannot continue forever. Every star follows the laws of physics with extraordinary consistency. Those laws allow astronomers not only to understand how stars shine today, but also to predict with remarkable confidence how they will evolve over billions of years. The sun still appears unchanged to our eyes, but deep within its core, invisible to every telescope, the future is already unfolding. The process that will one day transform the solar system has been underway since long before Earth itself was born. If that transformation has already begun, then perhaps the real question is not when the sun will die. Perhaps the more important question is whether we have already entered the first moments of its ending. The most dramatic events in the universe often begin so quietly that for a very long time they're impossible to notice. A mountain rises only a few millimeters each year. Yet over millions of years it reshapes an entire continent. A glacier advances so slowly that no traveller witnesses its movement, yet given enough centuries it carves valleys through solid rock. The sun belongs to this same category of change. Its transformation is measured not in years or centuries but in millions and billions of years. To every generation that has ever lived it has appeared eternal. Yet modern astronomy reveals that the sun today is not quite the same star that illuminated the young Earth more than 4 billion years ago. It is in fact brighter. The difference is surprisingly large. When the solar system first formed, the newborn sun produced only about 70% of the energy it radiates today. At first glance, that seems impossible. If our planet received nearly 1/3 less sunlight, Earth should have been a frozen world covered in ice from pole to pole. Oceans should have remained locked beneath glaciers. The chemistry necessary for life should have struggled to begin. And yet the geological record tells a different story. Ancient rocks preserve evidence that liquid water flowed across Earth's surface very early in its history. Minerals formed only in warm, wet environments appear in rocks more than 4 billion years old. Sedimentary formations suggest rivers, coastlines, and shallow seas. Even more remarkably, some of the earliest traces of life seem to date back to a time when the sun was supposedly far weaker than it is now. This contradiction became known as the faint young sun paradox. The paradox is not merely an interesting puzzle about Earth's distant past. It is one of the first clues that habitability depends on far more than the brightness of a star alone. Scientists now believe that Earth's early atmosphere was very different from today's. Higher concentrations of greenhouse gases, including carbon dioxide and possibly methane, trapped far more heat than our modern atmosphere does. Those gases acted like an enormous insulating blanket, allowing liquid water to persist despite the weaker sunlight. The solution reminds us of an important principle. A planet's climate is not controlled by a single factor. It emerges from a delicate balance involving stellar energy, atmospheric chemistry, geological activity, cloud formation, ocean circulation, and even the evolution of life itself. That balance has shifted many times throughout Earth's history. Ice ages have come and gone. Continents have drifted across the globe. Volcanoes have altered atmospheric composition. Living organisms themselves transform the atmosphere by releasing oxygen through photosynthesis. Earth has never been completely static. Neither has the sun. Although the sun still appears almost perfectly constant, astronomers can measure subtle changes with extraordinary precision. Modern satellites continuously monitor its brightness, magnetic field, solar wind, and oscillations beneath the visible surface. Tiny variations reveal that the sun behaves less like a fixed light bulb and more like a dynamic, evolving sphere of plasma. Every 11 years, its magnetic field reverses polarity. Sunspots increase and then decline. Solar flares become more or less frequent. These cycles influence space weather throughout the solar system, occasionally disrupting satellites, electrical systems, and radio communications here on Earth. Yet these familiar cycles are only surface rhythms. Far beneath them, something much slower is happening. As hydrogen disappears from the core, helium gradually accumulates. Helium is denser than hydrogen, causing the central regions of the sun to contract under gravity. That contraction raises both temperature and pressure inside the core. Higher temperatures accelerate nuclear fusion. Faster fusion produces more energy. More energy slowly increases the sun's overall brightness. This process is extraordinarily gradual, but it never stops. On average, astronomers estimate that the sun becomes roughly 1% brighter every 100 million years. 1% sounds almost insignificant. No person could notice it. No civilization could measure it without extremely precise instruments and observations spanning immense lengths of time. Yet over geological timescales, those tiny increases accumulate. A 1% change repeated again and again eventually transforms an entire planetary system. This realization changes how we think about stability. The solar system is often described as a remarkably peaceful place. Planetary orbits remain nearly unchanged over millions of years. The sun rises each morning, seasons repeat with dependable regularity. These rhythms encourage the comforting impression that nature prefers permanence. Physics suggests something different. Nature often favors slow evolution rather than permanent equilibrium. Stable systems remain stable only because countless small adjustments continuously maintain their balance. Eventually, those adjustments lead somewhere new. Astronomers have found compelling evidence for this principle beyond our own solar system. Thousands of exoplanets now reveal astonishing diversity. Some orbit stars hotter than the Sun. Others circle cool red dwarfs. Some complete an orbit in only a few days. Others take centuries. Many worlds appear to have experienced runaway greenhouse effects. Others may once have possessed oceans that later vanished into space. These distant planetary systems allow astronomers to see versions of futures that our own solar system has not yet reached. Venus provides one example much closer to home. Today, Venus is the hottest planet in the solar system, even though Mercury lies closer to the Sun. Its thick atmosphere traps heat so efficiently that surface temperatures approach 465 degrees Celsius, hot enough to melt lead. Yet many planetary scientists suspect that billions of years ago, Venus may have possessed shallow oceans and a much milder climate. If that hypothesis is correct, Venus represents a cautionary lesson. A planet does not need its star to explode in order to become uninhabitable. Sometimes the star changes only slightly. The planet does the rest. This possibility naturally turns our attention back toward Earth. Climate models suggest that long before the Sun enters its dramatic final stages, increasing solar brightness will gradually intensify evaporation. More water vapor will enter the atmosphere. Because water vapor itself is a greenhouse, gas warming will accelerate further. Eventually, over immense spans of time, Earth's oceans could begin disappearing into space as ultraviolet radiation breaks water molecules apart and lightweight hydrogen escapes Earth's gravity forever. This is not a prediction for the next century or the next million years. It belongs to timescales measured in hundreds of millions and billions of years. Human civilization will never witness these changes unfolding directly, yet physics indicates that they are already part of Earth's future. Here lies another paradox. The Sun's greatest gift to life is its steady supply of energy. Yet that very stability slowly carries within it the seeds of future instability. The brighter the Sun becomes, the more difficult it becomes for Earth to remain the world we know. Remarkably, none of this depends upon catastrophe. No giant explosion. No sudden collapse. No violent cosmic accident. Only the patient, almost imperceptible consequences of ordinary stellar evolution. For much of history, people imagined that the end of the world would arrive suddenly announced by fire from the heavens or unimaginable disaster. Astronomy offers a quieter vision. The first signs of Earth's distant uninhabitability may unfold so gradually that no single generation could recognize them without comparing themselves to ancestors separated by millions of years. That quietness makes the story even more profound. The universe rarely hurries. It simply continues. And as astronomers began recognizing these first cracks in the apparent permanence of the Sun, they were forced to ask an even deeper question. If every ordinary star must eventually change, who first uncovered this hidden pattern? And how did humanity learn that the lives of stars themselves could be read almost like biographies written across the night sky? For most of human history, the stars appeared timeless. They rose in the same constellations, followed the same seasonal paths, and seemed to watch silently over generations that came and went beneath them. Empires expanded and disappeared. Languages evolved. Religions were born. Yet the night sky appeared almost unchanged. It was natural to believe that the stars themselves belonged to a perfect and unchanging universe. Even after the invention of the telescope, that assumption survived. Astronomers could resolve planets into worlds, discover moons circling Jupiter, and observe mountains on the moon. But the stars remained stubbornly mysterious. They were simply too far away. Even the largest telescopes of the 18th century showed them only as brilliant points of light. How could anyone hope to understand the life of an object that could not even be seen as a disk? The answer did not come from looking at a single star. It came from looking at many. One of the great strengths of science is that it often discovers patterns where individual examples reveal very little. A single tree tells us almost nothing about the life cycle of forests. A single human life cannot explain the evolution of civilizations. But when thousands or millions of examples are observed together, hidden relationships begin to emerge. The same proved true for the stars. During the 19th century, telescopes became increasingly powerful, but an equally important revolution occurred in a different field. Light itself became a scientific tool. When sunlight passes through a glass prism, it spreads into a rainbow of colours. This simple observation had been known since the work of Isaac Newton, but later scientists discovered that the rainbow contained something even more remarkable. It was not continuous. Tiny dark lines crossed the spectrum. At first, these lines seemed like little more than curiosities, but careful experiments revealed that every chemical element absorbs and emits light at very specific wavelengths. Hydrogen leaves one pattern, helium leaves another. Sodium, calcium, iron, and oxygen each possess their own unmistakable signatures. A star's light, once thought to reveal almost nothing, suddenly became a remarkably detailed record of its physical nature. Without ever touching a star, astronomers could determine what it was made of. Soon they learned even more. The colour of a star revealed its temperature. Blue stars burned hotter. White stars were somewhat cooler. Yellow stars, including our own sun, occupied a middle range. Orange and red stars radiated less energy from their surfaces. Each colour reflected conditions governed by the same laws of physics that could be reproduced in laboratories on Earth. For the first time, distant suns became understandable objects rather than unreachable lights. Yet the greatest breakthrough still lay ahead. At the beginning of the 20th century, astronomers were cataloguing enormous numbers of stars. Among them was Annie Jump Cannon, whose extraordinary ability to classify stellar spectra transformed observational astronomy. Working with photographic plates containing countless stars, she organised them according to the patterns hidden within their light. The sequence that emerged eventually became famous. O, B, A, F, G, K, M. The letters appear almost random today because they preserve the history of earlier classification systems, but together they describe stars from the hottest blue giants to the coolest red dwarfs. Our Sun belongs to the G class. It is neither especially hot nor especially cool, neither especially large nor especially small. Once again the Sun proved to be surprisingly ordinary. That ordinariness would soon become one of astronomy's greatest advantages. Another key figure entered the story. Einar Hertzsprung and independently Henry Norris Russell noticed something remarkable when they compared stars according to both their temperature and their brightness. If stars were scattered randomly, no clear pattern should have appeared. Instead, they clustered along a graceful curve. This relationship became known as the Hertzsprung-Russell diagram, often shortened to the HR diagram. At first glance, it looks almost deceptively simple. Temperature runs across one axis. Brightness rises along the other. Thousands of stars become tiny points on a graph. Yet hidden within that graph is one of the deepest discoveries in astronomy. The stars do not occupy every possible position. Most gather along a broad diagonal band called the main sequence. Others appear above it as swollen giants. Still others cluster below it as faint white dwarfs. The arrangement was far too orderly to be accidental. It suggested that stars were not random objects created in different forms. They were passing through different stages of a common life cycle. This idea was revolutionary. Instead of thinking of stars as fundamentally different kinds of objects, astronomers began to understand them as individuals at different ages. A child, an adult, and an elderly person may appear quite different, yet they belong to the same species and follow the same biological journey. Likewise, a blue main sequence star, a red giant, and a white dwarf were increasingly recognized as different chapters in the evolution of a single star. The question then became obvious. What drives that evolution? For a time no one knew. Gravity alone could not explain the immense energy radiated by stars over billions of years. Chemical burning was equally impossible. If the sun were powered by ordinary combustion, calculations showed it would exhaust its fuel in only a few thousand years, far too short for Earth's geological history. The mystery remained unresolved until the 20th century, when advances in atomic physics transformed astronomy once again. Researchers gradually realized that conditions inside stellar cores were unlike anything found naturally on Earth. Temperatures reached millions of degrees. Pressures became almost unimaginable. Under those extraordinary conditions, atomic nuclei could overcome their electrical repulsion and merge together. Nuclear fusion had entered the story. Hydrogen fused into helium. A tiny amount of mass disappeared. An enormous quantity of energy emerged. At last, the sun possessed a believable engine capable of sustaining its brilliance for billions of years. Just as importantly, fusion explained the pattern seen on the Hertzsprung-Russell diagram. A star spends most of its lifetime steadily burning hydrogen in its core. Eventually, that hydrogen becomes depleted. The balance between gravity and outward pressure begins to change. The star responds by evolving into entirely new forms. What had seemed like separate categories were actually successive stages governed by universal physical laws. Suddenly the universe acquired a sense of history. Stars had births. They experienced long periods of maturity. They grew old. They died. Even more remarkable astronomers realized that these stages unfolded according to a star's mass. Massive stars raced through their lives, exhausting their fuel in only millions of years before ending as supernovae and leaving behind neutron stars or black holes. Smaller stars burned much more slowly. The tiniest red dwarfs would outlive every other known type of star by astonishing margins. The sun fell comfortably between these extremes. Its future no longer seemed mysterious. Its path through the HR diagram could be calculated with increasing confidence. Not every detail was known, but the broad outline became clear. It would remain on the main sequence for billions more years. Then it would expand dramatically. Later it would shed its outer layers. Finally, only a dense white dwarf would remain. The prediction did not depend on observing our own sun change. No astronomer could wait billions of years. Instead, the universe itself supplied countless examples. Some stars were young, others were middle-aged. Still others had already reached stages our sun would not experience for billions of years. Looking across the galaxy was like opening a library whose shelves contained every chapter of the same story. Some books had only begun, others were nearly finished. Together they revealed the entire narrative, and that narrative carried profound consequences. For the first time, humanity understood that the sun's future was not an isolated event. It belonged to a universal pattern written into the very physics of matter and energy. The question was no longer whether the sun would change. That had become one of astronomy's strongest conclusions. The real question now was how those changes would reshape the worlds orbiting around it. If the sun's destiny could already be read among the stars, what would Earth look like as our familiar yellow star slowly began its transformation into something far larger, hotter, and far less hospitable? Knowing that the sun will eventually change is one thing. Understanding what those changes mean for the worlds that orbit it is something altogether different. When people picture the death of the sun, they often imagine a single catastrophic event, a brilliant explosion, a sudden darkness, a moment when everything familiar ends at once. That image owes much to the spectacular deaths of massive stars whose lives conclude in supernovae visible across entire galaxies. Our sun will not follow that path. Its ending will be quieter, slower, and in some ways far more unsettling. Nothing dramatic will happen tomorrow. Nothing remarkable will happen next century. Even 1,000,000 years from now, the solar system will appear comfortingly familiar to any observer who could stand upon Earth. The continents will have shifted. Mountains will have risen and eroded. Countless species will have appeared and vanished. Yet the sun itself will still shine as a steady yellow star. The great transformation belongs to a future almost impossible for the human mind to grasp. By about 1 billion years from now, however, the Sun's gradual increase in brightness will begin producing consequences that no planetary process can fully counteract. The Earth will still orbit at essentially the same distance. Its gravitational relationship with the Sun will remain nearly unchanged, but the amount of energy arriving each second will have increased enough to begin altering the planet in profound ways. At first, the changes may seem surprisingly subtle. Warmer oceans release more water vapor into the atmosphere. Water vapor is itself a powerful greenhouse gas, trapping additional heat and reinforcing the warming already caused by the brighter sun. This creates a positive feedback loop. More heat produces more vapor traps more heat. The cycle continues slowly but persistently. Unlike modern discussions of climate over decades or centuries, these processes unfold across hundreds of millions of years. The physics is familiar. The timescale is extraordinary. Climate models suggest that eventually Earth's oceans will begin evaporating faster than they can remain stable. Clouds may temporarily reflect some additional sunlight, slowing the warming, but only for a time. As temperatures continue rising, the atmosphere becomes increasingly humid. Higher in the atmosphere, ultraviolet radiation from the sun begins breaking apart water molecules. Hydrogen, being the lightest element in the universe, escapes Earth's gravity with relative ease. Oxygen reacts with rocks and minerals or is carried away by other chemical processes. Little by little, Earth's water inventory begins shrinking. The oceans are not boiled away overnight. Instead, they slowly leak into space. It is one of the quietest planetary catastrophes imaginable. From a human perspective, nothing appears urgent. From a geological perspective, everything has already changed. Long before the last ocean disappears, the biosphere itself begins to contract. Complex plants struggle under rising temperatures. Forests retreat. Food webs become increasingly fragile. Animals dependent upon abundant surface water face mounting challenges. Eventually, the familiar richness of Earth's ecosystems gives way to isolated pockets where life can still endure. Some microorganisms may survive deep underground or within protected environments long after surface conditions become hostile. Life has proven remarkably resilient throughout Earth's history. It has survived asteroid impacts, global glaciations, immense volcanic eruptions, and dramatic shifts in atmospheric chemistry. Yet every form of life depends ultimately upon certain physical limits. No ecosystem can flourish indefinitely on a world whose surface continues warming without relief. The remarkable point is that none of this requires the sun to become a red giant. Earth's habitability begins ending while the sun is still recognizably the sun. The first true deadline for our planet arrives billions of years before the final chapter of stellar evolution. Mars, meanwhile, experiences a different future. Today it is a cold desert. Its thin atmosphere provides little protection against freezing temperatures. Liquid water is unstable across most of its surface. But as solar energy gradually increases, Mars may briefly become more hospitable than it is today. Ice locked beneath its surface could melt. Frozen carbon dioxide trapped at the poles might enter the atmosphere, thickening it somewhat. Temperatures would rise. For a limited period, portions of Mars might support liquid water far more easily than they do now. It would not become another Earth. Its lower gravity, lack of a global magnetic field and limited atmosphere would still present enormous challenges. Yet in the distant future, Mars may pass through a comparatively favourable chapter while Earth enters decline. This reversal is one of the most intriguing consequences of stellar evolution. The habitable zone, often described as the region around a star where liquid water can exist, is not fixed. It moves. As the sun slowly brightens, that invisible ring of potentially habitable environments drifts steadily outward. Worlds that are currently too cold may eventually receive enough warmth to become more accommodating. Worlds that are presently comfortable gradually become too hot. The habitable zone is therefore less like a permanent address and more like a slowly moving shoreline. Any planet hoping to remain within it must either migrate or accept that favourable conditions are temporary. Beyond Mars lie the giant planets and their many moons. Jupiter itself, being composed mostly of hydrogen and helium, offers no solid surface upon which people could stand. Its immense gravity and violent atmospheric pressures make it profoundly inhospitable. Yet some of its moons tell a different story. Europa hides a vast ocean beneath an icy shell. Ganymede possesses its own magnetic field unique among moons in the solar system. Callisto appears geologically quiet and may preserve enormous quantities of ice. Farther still, Saturn's moon Titan possesses rivers and lakes, though not of water but of liquid methane and ethane. Beneath its frozen crust, many scientists suspect another hidden ocean of liquid water. Today, these distant worlds exist in deep cold because the sun's warmth diminishes rapidly with distance. As the sun grows brighter, however, the outer solar system changes alongside the inner planets. Ice melts. Surface temperatures rise. Previously frozen environments become more dynamic. Some moons may spend hundreds of millions of years inside the expanding habitable zone. This possibility has inspired generations of planetary scientists. Rather than asking whether Earth alone can support life forever, they increasingly examine the solar system as a sequence of opportunities unfolding over immense spans of time. The center of habitability does not remain fixed. It slowly migrates outward, carrying with it new possibilities and new challenges. Still, these opportunities come with limits. The sun is not merely becoming brighter. Its internal structure continues evolving. Eventually, hydrogen in the core becomes so depleted that the long period of stable fusion comes to an end. Gravity begins winning the delicate balance it has contested for billions of years. The core contracts. Temperatures rise dramatically. Fusion shifts into surrounding layers. The outer regions respond in a way both beautiful and terrifying. The sun begins to swell. At first, the expansion is gradual. Then, over astronomical timescales, it becomes unmistakable. Its diameter increases. Its luminosity climbs enormously. The familiar yellow star slowly transforms into something entirely different. A red giant. Seen from a distant planetary system, it would still be recognizable as the same star. Seen from within the solar system, it would redefine everything. Mercury's orbit lies deep within the expanding stellar atmosphere. Venus almost certainly shares the same fate. Whether Earth itself is ultimately engulfed remains an active area of research. Some models suggest that the Sun's outer layers may extend beyond Earth's present orbit. Others indicate that mass lost by the Sun could allow Earth's orbit to drift outward, just enough to escape direct engulfment. Either outcome leads to the same practical conclusion. By then, Earth would already be uninhabitable. Its oceans long vanished, its atmosphere profoundly altered, its surface baked beneath a sky dominated by an enormous crimson sun occupying much of the heavens. The exact details remain uncertain. The broader picture does not. Earth's future as a living world ends long before the sun's life does. That realization transforms the original question. Perhaps humanity doesn't need to survive the death of the sun itself. Perhaps it must first survive the billions of years leading up to that death. And that raises an entirely different mystery. If Earth cannot remain our permanent home, could humanity truly become a civilization of many worlds before the clock finally runs out? For most of history, humanity asked a remarkably simple question about survival. Could we endure the next winter? Later, the question grew larger. Could a city survive a famine? Could a nation survive a war? Only within the past century has our perspective expanded enough to ask something entirely different. Could an entire civilization survive the evolution of its own star? This is where the documentary's central mystery truly begins. Until now, we have followed evidence that is broadly accepted within astronomy. The sun is slowly becoming brighter. Earth will eventually lose the conditions that have supported complex life. Billions of years from now, the sun will leave the stable main sequence and begin its transformation into a red giant. These conclusions rest upon decades of observation stellar modeling nuclear physics and comparisons with countless other stars. The mystery lies beyond them. If Earth has an expiration date, what exactly must humanity preserve? At first, the answer seems obvious. We must preserve ourselves. But even that simple statement becomes surprisingly difficult to define. Does humanity mean a particular planet, a particular species, a biological form, a culture? Or does it simply mean an unbroken chain of conscious beings descended from those who first looked up at the night sky? Astronomy cannot answer philosophical questions. It can, however, establish the physical boundaries within which those questions must be asked. One of the most important lessons from planetary science is that planets themselves are temporary. Earth feels permanent because human lives are brief. From a cosmic perspective, every planet changes continuously. Continents drift across their surfaces. Atmospheres evolve. Magnetic fields strengthen and weaken. Oceans appear and disappear. Even the orbits of planets experience tiny gravitational adjustments over immense spans of time. The solar system is remarkably stable, but it is not frozen. Nothing in astronomy suggests that planets are eternal homes. Instead, they appear more like chapters in much longer stories. This realization leads naturally to another possibility. Perhaps civilization should be thought of in the same way. For nearly all of human history, civilization and planet have been inseparable concepts. Every language, every ecosystem, every technological achievement, every work of art has emerged within Earth's thin atmosphere. Even our imagination is shaped by gravity, weather, daylight, and seasons unique to this world. It is difficult to picture humanity existing anywhere else, because every human experience has been filtered through Earth. Yet the first small cracks in that assumption have already appeared. Astronauts have lived aboard orbiting space stations for months at a time. Robotic explorers have operated successfully on Mars. Spacecraft have landed on comets flown past Pluto, entered interstellar space, and visited nearly every major world in the solar system. Each mission demonstrates a simple but profound truth. The boundary separating humanity from the rest of space is no longer absolute. It is technological. Technology cannot repeal the laws of physics. It cannot make vacuum disappear or eliminate radiation, but it can create temporary environments in which those laws become manageable. A spacecraft is in many ways a tiny artificial planet. Its walls replace an atmosphere. Its life support systems replace natural ecosystems. Its structure protects delicate biological life from an environment that would otherwise be fatal within seconds. Every successful space mission is therefore more than an engineering achievement. It is a proof of concept. Human beings can survive away from Earth provided they bring enough of Earth's environment with them. The obvious objection follows immediately. A spacecraft can support a handful of people. How could it ever sustain millions or billions? This question has occupied scientists, engineers, and futurists for decades. Importantly, the discussion remains grounded in physics rather than fantasy. No accepted scientific theory forbids the construction of very large space habitats. The challenges are enormous, but they arise from engineering complexity rather than violations of natural law. One of the earlier serious proposals came from the American physicist Gerard K. O'Neill during the 1970s. Instead of focusing exclusively on settling planets, O'Neill asked a different question. What if the best place for future civilizations was not on planets at all? He envisioned enormous rotating habitats built in space. Their rotation would create artificial gravity through centrifugal force. Large mirrors would direct sunlight into agricultural regions. Closed ecological systems would recycle water, air, and nutrients. Residents might one day experience forests, rivers, neighborhoods, and open skies inside structures drifting peacefully between the planets. At the time, these ideas seemed extraordinarily ambitious. In many respects, they still are. No such habitat has yet been constructed. This distinction is important. The concept belongs to engineering proposals supported by known physics. Its feasibility at large scales remains untested. Fact: artificial gravity through rotation is consistent with physics. Evidence: closed ecological systems have been demonstrated on limited scales aboard spacecraft and in experimental facilities on Earth. Hypothesis: entire self-sustaining cities could eventually operate for centuries or millennia in space. Unknown: whether such systems can remain biologically, socially, and technologically stable over geological timescales. Separating these categories helps preserve scientific honesty. The universe is already mysterious enough. It needs no exaggeration. Even without giant habitats, another possibility emerges. Rather than moving all of humanity at once, civilization could gradually expand. Permanent settlements might first appear on the Moon, later on Mars, eventually among the asteroids. Mining operations could obtain metals and water directly from space rather than launching every resource from Earth. Solar power satellites might collect continuous sunlight without atmospheric interruption. Manufacturing could increasingly occur beyond Earth's gravity well. None of these ideas guarantees success. They simply illustrate that leaving Earth need not happen in one dramatic migration. It could unfold over thousands or even millions of years. Human history already offers a distant analogy. Our ancestors did not spread across Earth in a single generation. Migration occurred slowly. Groups settled new environments. Cultures diverged. Technologies adapted to different climates. Over time, an African species became a planetary civilization. Could a planetary civilization one day become a solar system civilization by similar gradual expansion? Astronomy offers no certainty, only possibility. There is another reason this gradual approach matters. The sun's increasing brightness is not an immediate emergency. Humanity possesses, at least according to current stellar models, roughly another billion years before Earth's surface becomes seriously threatened by the long-term effects of solar evolution. A billion years. That span exceeds the entire history of complex multicellular life on Earth. It is approximately 200,000 times longer than recorded human history. Viewed this way, the challenge begins to look less like a desperate escape and more like a long developmental process. The real question is not whether humanity can invent one miraculous technology. It is whether civilization can continue advancing, recovering from setbacks, preserving knowledge, and expanding steadily across unimaginably long periods of time. That may prove to be the greater difficulty. Stars evolve predictably. Civilizations do not. Empires collapse. Knowledge can be lost. Environmental changes, natural disasters, conflicts, and unforeseen events can interrupt even the most successful societies. Astronomy gives humanity time. History reminds us that time alone guarantees nothing. Perhaps the greatest obstacle to surviving the sun is not physics. Perhaps it is continuity. Can one civilization remain connected to its descendants across millions of generations? Can purpose survive longer than memory? Can curiosity endure longer than nations? These questions cannot yet be answered by telescopes, but they prepare us for the next stage of the journey. Because if humanity truly hopes to outlive Earth, the first destination may not be another star. It may simply be the many unexplored worlds already circling our own. If Earth cannot remain humanity's permanent home, the next question seems almost inevitable. Where would we go? For centuries, this question belonged almost entirely to fiction. Distant planets were blank worlds onto which writers could project hope, danger, or adventure. Mars was imagined as a dying civilization. Venus became a steaming jungle. The moons of Jupiter were little more than names in astronomical catalogues. Today that landscape has changed. Robotic explorers have transformed nearly every major world in the solar system from an object of speculation into a place with measurable geology, chemistry, climate, and history. Ironically, the more we have learned, the more complicated the answer has become. There is no second Earth waiting quietly nearby. Every world offers possibilities. Every world presents formidable obstacles. The evidence must be examined carefully, one destination at a time. The Moon is the obvious place to begin. It is Earth's constant companion, orbiting at an average distance of only about 384,000 kilometers. Signals travel between Earth and the Moon in little more than a second. Spacecraft can reach it in a matter of days rather than months or years. From the perspective of logistics, no other celestial body comes close, yet proximity alone does not make it hospitable. The Moon possesses almost no atmosphere. Without air, there is no meaningful protection from solar radiation or micrometeoroids. Temperatures swing from roughly 120 degrees Celsius during the lunar day to about minus 130 degrees Celsius during the night. Its gravity is only 1/6 that of Earth's. Scientists still do not know whether humans could remain healthy after living under such reduced gravity for many generations. Short-term missions demonstrate that people can function there for days or weeks. Whether entire civilizations could adapt over centuries remains an open question. Nevertheless, the Moon possesses one invaluable resource: water. For decades, astronomers suspected that permanently shadowed craters near the lunar poles might preserve ancient ice deposited by comets and asteroids. Modern spacecraft confirmed those suspicions. That discovery transformed scientific thinking. Water is not merely something to drink. It can be purified, recycled, used to grow food, separated into hydrogen and oxygen for rocket fuel, and employed as additional shielding against radiation. A lunar settlement with reliable access to ice would possess one of the most precious resources in space. The Moon therefore represents less a final destination than an ideal proving ground. If humanity cannot build self-sustaining communities only a few days from Earth, it is difficult to imagine doing so around another star. Beyond the Moon lies Mars. No other planet has inspired such sustained scientific interest. Unlike the Moon, Mars once possessed rivers, lakes, and perhaps even shallow seas. Ancient valleys stretch across its surface. Delta formations resemble those created by flowing water on Earth. Minerals that form only in the presence of liquid water have been identified across wide regions. The evidence paints a remarkably consistent picture. Billions of years ago, Mars was warmer and wetter than it is today. Its transformation raises profound questions. If two neighbouring planets began with somewhat similar ingredients, why did one remain habitable while the other became a frozen desert? The answer appears to involve several interconnected factors. Mars is much smaller than Earth. Its weaker gravity made it more difficult to retain a thick atmosphere over billions of years. Its internal heat diminished more rapidly, weakening the global magnetic field that once helped protect the atmosphere from the solar wind. Gradually, the atmosphere thinned, surface pressure fell, liquid water became increasingly unstable. The planet entered the cold, arid state observed today. Yet Mars still offers advantages unavailable almost anywhere else in the solar system. Its day lasts only about 40 minutes longer than Earth's. Water ice exists beneath the surface and at the poles. Its atmosphere, though thin, contains abundant carbon dioxide that could potentially support plant growth inside controlled habitats. Its gravity, while only about 38% of Earth's, is significantly stronger than the Moon's. Because of these characteristics, Mars occupies a unique position. It is not comfortable. It is workable. Current engineering studies envision habitats buried beneath the surface covered with regolith to reduce radiation exposure. Underground lava tubes formed during the planet's volcanic past may provide enormous natural caverns requiring relatively little excavation. Such ideas remain proposals rather than established achievements. No permanent human settlement yet exists on Mars. Still, each robotic mission adds new information that gradually replaces uncertainty with measurable knowledge. Leaving Mars behind the solar system becomes increasingly unfamiliar. The asteroid belt is often portrayed as a crowded obstacle course in films, but reality is much quieter. Individual asteroids are separated by immense distances. Most spacecraft pass through the belt without coming anywhere near another object. Its true significance lies elsewhere. Asteroids preserve vast quantities of raw materials: iron, nickel, silicates, carbon-rich compounds, water ice within certain classes of asteroids. Mining these resources would avoid the enormous energy required to launch everything from Earth's deep gravitational well. Many researchers therefore view asteroids not as places where large populations would necessarily live, but as industrial centres supporting a much broader space-based economy. Then come the giant planets. Jupiter dominates the solar system with extraordinary gravity. More than twice as massive as all the other planets combined, it has shaped planetary evolution since the earliest days of solar system formation. Its cloud tops are beautiful. Its environment is unforgiving. Radiation trapped within Jupiter's immense magnetic field reaches levels that would rapidly prove fatal to unprotected humans. Its atmosphere grows denser with depth until pressures become immense. There is no solid surface upon which a city could be built. Yet Jupiter's moons tell an entirely different story. Europa has fascinated planetary scientists for decades. Its bright icy surface appears smooth from a distance, but close observations reveal networks of cracks stretching across the crust. Beneath that shell lies compelling evidence for a global ocean containing more liquid water than all of Earth's oceans combined. No one knows whether that hidden ocean contains life. No direct evidence has yet been found. Nevertheless, Europa remains one of the most promising places in the solar system to search for biology beyond Earth. For future human exploration, however, another challenge emerges. Jupiter's radiation environment extends far beyond the planet itself. Any long-term settlement near Europa would require substantial protection. Ganymede presents a somewhat different case. It is the largest moon in the solar system, even larger than the planet Mercury. Uniquely among moons, it possesses its own magnetic field, offering at least partial shielding from charged particles. Callisto, orbiting still farther away, experiences significantly lower radiation levels than Europa or Ganymede. For this reason, some mission concepts identify Callisto as a potentially safer location for distant human outposts. Farther outward, Saturn introduces one of the most intriguing worlds known. Titan, wrapped in a thick nitrogen atmosphere denser than Earth's in terms of surface pressure, Titan possesses lakes, rivers, rainfall, and weather. But there is a remarkable difference. Its rivers are not water, its lakes are not oceans. At Titan's frigid temperatures, methane and ethane exist as liquids, creating a hydrological cycle unlike anything on Earth. Water there behaves almost like rock. Yet beneath Titan's frozen crust, multiple lines of evidence suggest another hidden ocean, composed primarily of liquid water mixed with other substances. Titan offers several advantages. Its atmosphere provides excellent protection from radiation. Its abundant organic molecules could prove valuable for future industry. Its low gravity would simplify launches back into space. At the same time, sunlight at Saturn's distance is roughly 1% as intense as it is on Earth. Energy becomes a central challenge. Every destination requires trade-offs. Closer worlds receive abundant sunlight but face increasing heat as the sun evolves. More distant worlds remain colder but possess greater long-term potential as the habitable zone slowly migrates outward. Astronomers increasingly view the solar system not as a collection of isolated planets, but as a sequence of environments whose relative suitability changes over billions of years. In effect, the entire solar system evolves alongside the sun. The evidence points toward a remarkable conclusion. Humanity may never need to leap directly from Earth to another star. Between our homeworld and interstellar space lies an entire archipelago of possible stepping stones. Each offers lessons. Each demands new technologies. Each expands the range within which civilization can exist. Yet another question quietly waits beyond them. Even if humanity succeeds in spreading across many worlds, every one of those worlds still remains bound to the same aging sun. Would becoming a multi-planet civilization truly solve the problem, or merely postpone it? Spreading across the solar system is often presented as though it were a single solution. In reality, it is a collection of very different ideas, each built upon its own assumptions about physics, engineering, economics, biology, and even human nature. Astronomy can tell us which worlds exist. Engineering can estimate what might be built. But when we ask how humanity could survive for billions of years, we enter a landscape where established knowledge gradually gives way to carefully reasoned possibility. This distinction matters. Throughout this journey, it is important to separate four categories: observed fact, measured evidence, scientific hypothesis, unknown. Only by keeping those boundaries clear can we appreciate both the remarkable progress of modern science and the immense mysteries that remain. One possibility is the most intuitive. Move civilization from one planet to another. This planetary migration model assumes that humanity will always prefer living on natural worlds. Planets provide gravity landscapes, horizons, and geological resources. They require fewer artificial systems than completely constructed habitats. Evidence supporting this idea already exists. Earth demonstrates that planets can support complex ecosystems over billions of years. Mars preserves water minerals and accessible terrain. Certain moons contain abundant ice and other valuable materials. These are measurable facts. The hypothesis is that future engineering could transform some of these environments into places capable of supporting large populations. This process is often called terraforming. Terraforming does not mean making another planet identical to Earth. Rather, it refers to gradually altering atmospheric composition, temperature, and surface conditions until they become more favorable for life. Mars has long been the primary focus of such discussions. Some proposals suggest releasing greenhouse gases trapped within the Martian surface or manufacturing powerful artificial greenhouse compounds to warm the planet. Others envision enormous orbital mirrors reflecting additional sunlight onto the polar regions, releasing frozen carbon dioxide to thicken the atmosphere. Each proposal is grounded in known physical principles. Whether any can succeed at planetary scales remains uncertain. Current evidence suggests that Mars may not possess enough accessible carbon dioxide to generate a dense Earth-like atmosphere, even if every known reservoir were released. That finding illustrates an important lesson. Ideas can be scientifically reasonable without being practically achievable. The difference between possibility and feasibility is often enormous. A second vision begins from a completely different assumption. Instead of changing planets, change where people live. This is the concept behind large artificial habitats. Unlike terraforming, which attempts to reshape an entire world, space habitats create controlled environments, only as large as needed. Their greatest advantage lies in flexibility. Artificial gravity can be generated through rotation. Temperature can be carefully regulated. Atmospheric composition can be optimized. Population density can expand by constructing additional habitats rather than altering an entire planet. Many engineers point out another subtle benefit. Launching from planets always requires escaping gravity. Habitats built in free space avoid that challenge. Transportation between them could require much less energy than repeatedly climbing out of deep planetary gravity wells. Evidence supporting this concept comes from physics itself. Rotating structures do produce apparent gravity. Closed recycling systems already function aboard spacecraft, although on much smaller scales. Solar energy remains abundant throughout much of the inner solar system. Unknowns remain substantial. Can ecosystems remain biologically stable for thousands of years? How large must habitats become before they feel psychologically comfortable? How would societies govern themselves when separated by millions of kilometers? No experiment has yet lasted long enough to answer these questions. A third possibility shifts attention away from places entirely. Perhaps the true home of future civilization is movement. Interstellar travel has traditionally been viewed as impossible because the distances are so overwhelming. The nearest star system beyond the Sun lies more than 4 light-years away. At the speeds achieved by today's spacecraft, such a journey would require tens of thousands of years. This fact is firmly established, yet physics does not forbid travel between stars. It merely places demanding constraints upon energy, propulsion, and time. Several concepts have been studied seriously. Nuclear fusion propulsion could potentially achieve much higher velocities than conventional chemical rockets. Matter-antimatter reactions possess even greater theoretical energy densities, although producing and storing useful quantities of antimatter remains an immense technological challenge. Solar sails and laser-driven light sails offer another approach, accelerating lightweight spacecraft using radiation rather than onboard fuel. These concepts differ dramatically in maturity. Fact: light exerts pressure. Evidence: solar sails have successfully flown in space. Hypothesis: powerful ground or space-based lasers might one day accelerate probes or perhaps larger vehicles to significant fractions of light speed. Unknown: whether such systems can ever transport large human populations economically. Each idea occupies a different position along the spectrum from demonstrated reality to informed speculation. Another proposal addresses the problem from the opposite direction. Instead of traveling faster, travel longer. Generation ships represent one of the oldest scientifically grounded concepts for interstellar migration. Rather than expecting one crew to reach another star within a normal human lifetime, the spacecraft itself becomes a miniature civilization. Children are born during the journey. Grandchildren continue it. Many generations pass before arrival. Physics places no obvious prohibition upon such missions. Human sociology presents a much greater uncertainty. Can a community remain stable for centuries while isolated in deep space? Would later generations still feel committed to the mission begun by distant ancestors? How would education preserve technical knowledge across so many lifetimes? These questions remain almost entirely unexplored. No human society has ever attempted such an undertaking. Closely related are suspended animation and long-term hibernation. Many animals on Earth dramatically reduce their metabolism during unfavorable seasons. Scientists continue studying whether similar techniques might one day become medically practical for extended human spaceflight. Current research explores short-term therapeutic hypothermia and metabolic suppression. No existing technology can safely place humans into centuries-long suspended animation. It therefore remains speculative. Perhaps the most ambitious proposal of all involves sending information rather than bodies. Human knowledge culture or even complete biological instructions might someday be transmitted across interstellar distances, allowing reconstruction elsewhere, using local materials. This concept appears frequently in discussions of future technology. At present, it remains almost entirely hypothetical. It depends upon advances far beyond current scientific capability. Recognizing this uncertainty is essential. Speculation can inspire research. It should never be mistaken for evidence. As these competing ideas accumulate, an unexpected pattern emerges. None of them promises certainty. None eliminates every obstacle. Each solves certain problems while introducing entirely new ones. Terraforming reduces dependence upon artificial habitats, but demands planetary-scale engineering. Artificial habitats provide flexibility but require continuous technological maintenance. Generation ships avoid impossible acceleration yet create profound social challenges. Interstellar propulsion shortens travel time but demands extraordinary energy. The universe offers no effortless path. It offers choices. Another realization gradually becomes apparent. Perhaps survival does not require selecting only one strategy. Human history rarely advances through single solutions. Agriculture didn't replace hunting overnight. Ships did not eliminate roads. Airplanes did not replace railways. Different technologies coexist because each serves different purposes. The same may prove true on cosmic scales. Future civilization could occupy planets' orbital habitats, mining stations, research outposts, and eventually interstellar vessels simultaneously. Diversity itself may become a form of resilience. A civilization distributed across many environments would be far less vulnerable than one concentrated upon a single world. That observation leads naturally to another thought experiment. Suppose one of these pathways succeeds. Suppose humanity establishes permanent communities beyond Earth. Suppose billions of people eventually live throughout the solar system. What would daily life actually become inside a civilization no longer dependent upon a natural planet? Would such a society still recognize itself as human? Or would survival gradually transform humanity in ways no previous generation could have imagined? A city is often defined by its buildings. A civilization is more accurately defined by the systems that allow those buildings to remain alive. Fresh water flows through pipes. Food arrives from distant fields. Electricity travels across power grids. Waste is removed before it becomes dangerous. Air remains breathable. Countless invisible processes operate together so reliably that most people rarely notice them. On Earth, these systems are supported by something even larger: the planet itself. Gravity keeps the atmosphere in place. The oceans regulate climate. Forests recycle carbon. Microorganisms enrich soils. The magnetic field deflects much of the charged radiation streaming outward from the sun. Life exists not because of one extraordinary feature, but because billions of interconnected processes reinforce one another. A civilization living beyond Earth would inherit none of these advantages for free. Everything that nature currently provides would have to be recreated, managed, or replaced. This is why many scientists argue that the greatest challenge of becoming a spacefaring civilization is not transportation. It is ecology. The first generations of orbital stations already revealed part of this lesson. Keeping astronauts alive for months is not simply a matter of carrying enough food and oxygen. Air must be continuously purified, carbon dioxide removed, water recovered from humidity, perspiration, and wastewater, microbial growth monitored. Tiny failures that would be minor inconveniences on Earth can become serious risks inside a completely enclosed habitat. Modern space stations recycle a significant fraction of their water and carefully manage every kilogram of supplies. These achievements demonstrate an important fact. Closed life support systems are possible. At the same time, they remain incomplete. Current systems still rely heavily upon regular resupply from Earth. A truly independent settlement would require something far more ambitious. Instead of simply recycling resources, it would need functioning ecosystems. Plants convert carbon dioxide into oxygen. Microorganisms break down waste. Pollinating insects or alternative technologies support food production. Nutrients circulate through carefully balanced cycles. Energy flows continuously into the system while matter remains largely contained within it. In essence, a successful space habitat must behave less like a building and more like a miniature planet. Scientists have already attempted small experiments in this direction. Perhaps the most famous was the project known as Biosphere 2 in the early 1990s. Researchers sealed several people inside an enclosed environment designed to recycle air, water, and nutrients while producing food internally. The experiment generated valuable scientific knowledge. It also revealed how extraordinarily complex real ecosystems are. Unexpected changes occurred in atmospheric chemistry. Certain species thrived while others declined. Pollination became difficult. Oxygen levels dropped for reasons that were not fully anticipated. The project demonstrated neither failure nor success in simple terms. Instead, it highlighted how much remained to be understood. Earth's biosphere is the product of billions of years of evolution. Reproducing its stability inside an artificial structure is an immense scientific challenge. That challenge becomes even greater over centuries. Mechanical systems wear out. Materials slowly degrade. Radiation damages electronics. Seeds evolve. Microorganisms mutate. Human societies themselves change. A habitat that functions well for 10 years may encounter entirely different problems after 100. After 1,000 years, the questions become almost philosophical. How do you preserve not merely machinery but knowledge? Human civilization has already experienced periods during which technologies were forgotten. Libraries burned, languages disappeared, engineering techniques were lost and later rediscovered. On Earth, neighbouring societies often preserved fragments of forgotten knowledge. A distant space habitat might possess no such safety net. Its survival could depend upon continuously teaching every new generation how the habitat itself functions. The spacecraft would not merely carry civilization, it would become civilization. This realization alters the meaning of infrastructure. A bridge can collapse without ending a nation. A failed agricultural season can often be compensated by imports. Inside an isolated habitat, however, the distinction between infrastructure and life nearly disappears. Air circulation is life. Water purification is life. Power generation is life. Ecological balance is life. Every maintenance task becomes part of survival itself. There is another challenge that receives increasing attention from researchers. Human biology evolved under one gravity, Earth's. Even with artificial gravity generated through rotation differences may remain. Would children born inside rotating habitats develop normally? How large must such habitats become before the curvature beneath one's feet becomes almost imperceptible? Could generations adapt psychologically to horizons enclosed by engineering rather than geology? Current evidence offers only partial guidance. Astronauts living for months in microgravity experience muscle loss. Bone density reduction, changes in vision and alterations to cardiovascular function. Regular exercise helps reduce these effects but does not eliminate them entirely. Artificial gravity remains one of the most actively discussed solutions precisely because prolonged weightlessness appears incompatible with lifelong health. Yet even if engineering solves gravity, another issue emerges: radiation. Earth's atmosphere and magnetic field absorb or deflect much of the high-energy radiation arriving from space. Outside those natural shields, cosmic rays and energetic particles become far more significant. Long-term exposure increases health risks and gradually damages living tissue. Engineers propose several protective strategies. Habitats could be covered by thick layers of water ice or lunar soil. Some concepts place living quarters deep inside excavated caverns. Others investigate active magnetic shielding inspired by Earth's own magnetosphere. Evidence supports the effectiveness of massive shielding. Whether artificial magnetic fields can provide practical large-scale protection remains an area of ongoing research. The distinction is important. Shielding by material is well understood. Large artificial magnetic shields remain largely theoretical. Meanwhile, daily life itself may gradually evolve. Food production might rely heavily upon hydroponics, aeroponics, cultured proteins, and highly efficient recycling rather than traditional agriculture. Windows could display carefully managed lighting cycles that simulate sunrise and sunset. Entire forests might exist within climate-controlled parks serving ecological, agricultural, and psychological functions simultaneously. Children could grow up seeing Earth not as home, but as the distant birthplace described in history lessons. Language would change. Architecture would change. Perhaps even concepts like weather seasons and wilderness would acquire new meanings. This possibility raises an unexpected question. Would future generations still wish to return to Earth? History suggests that identity often follows birthplace rather than ancestry. People born on different continents already develop distinct cultures while sharing common origins. The same pattern could eventually occur between worlds. Lunar communities, Martian settlements, orbital habitats, each adapting to local conditions while remaining connected through shared history. Astronomy cannot predict culture. It can only describe the environments within which cultures may emerge. One further realization slowly becomes unavoidable. Even a thriving civilization scattered across the solar system still depends upon one central source of energy: the sun. Solar panels, photosynthesis, climate, orbital mechanics. Nearly every aspect of solar system civilization ultimately traces back to the same star whose gradual evolution began this entire discussion. Artificial habitats may postpone dependence upon Earth. They do not eliminate dependence upon the sun. Unless humanity eventually reaches other stars, every city, habitat, and colony remains tied to the future of a single aging star. The challenge has therefore changed shape. It is no longer simply about surviving away from Earth. It has become a question of whether civilization itself can someday extend beyond the boundaries of the solar system. And that journey begins with an unexpected discovery. The stars most capable of supporting life for the longest periods are not the bright, familiar suns that dominate our night sky. They are the small, quiet stars that were once considered almost insignificant. The solar system has always felt immense. Neptune orbits the Sun at an average distance of nearly 4.5 billion kilometers. Light traveling at almost 300,000 kilometers every second still requires more than 4 hours to make that journey. Spacecraft launched from Earth have needed well over a decade to reach the outer planets. For generations, those distances define the limits of human imagination. Yet once we ask whether humanity can outlive the sun, the scale changes completely. The solar system, vast as it seems, becomes only the first neighborhood. Beyond it lies an ocean so large that even the nearer shores are difficult to comprehend. The closest known star system beyond the Sun is Alpha Centauri, located about 4.37 light-years away. To say that distance allowed is easy. To understand it is something else. A light-year is not a measure of time, but of distance. It is the span that light crosses in 1 year, almost 9.5 trillion kilometers. Multiply that by more than 4. The result is a separation so enormous that every planet ever discovered within our solar system could fit into the gap many thousands of times. Human experience offers no direct comparison. If the Earth were reduced to the size of a grain of sand, the Sun would be a small orange located several meters away. At that same scale, the nearest star would lie hundreds of kilometers distant. The night sky appears crowded only because depth disappears when viewed from so far away. In reality, the stars occupy an astonishing emptiness. This emptiness explains why interstellar travel is fundamentally different from journeys between planets. Within the solar system, gravity assists orbital mechanics, and relatively short communication delays allow missions to be planned with remarkable precision. Between stars, the distances themselves become the dominant challenge. Even radio messages require years to arrive. A conversation becomes impossible. A reply cannot return before nearly a decade has passed. Any civilization that expands into interstellar space must therefore become increasingly decentralized. Each settlement would gradually develop with far greater independence than cities separated by oceans on Earth. Physics itself encourages cultural divergence. The challenge begins with speed. Chemical rockets, the workhorses of the space age, are wonderfully effective for escaping Earth's gravity and exploring nearby worlds. They're entirely inadequate for crossing interstellar distances. The fastest spacecraft humanity has ever launched, Voyager 1, travels at roughly 17 kilometers per second relative to the Sun. That sounds extraordinarily fast. It is. Within the solar system, toward Alpha Centauri, however, such a speed would require more than 70,000 years, longer than all of recorded human civilization. Clearly another approach would be required. One possibility already exists in nature. The Sun itself continuously demonstrates it. Fusion. Every second, nuclear fusion converts mass into energy with astonishing efficiency. If controlled for propulsion rather than electricity, fusion could accelerate spacecraft to velocities far beyond those achievable using chemical fuels. Research into terrestrial fusion reactors continues today because of their potential as energy sources. Applying similar principles to spacecraft remains far more difficult, but it does not violate known physics. Fusion propulsion therefore occupies an intriguing position. Scientifically plausible, technologically unresolved. Another idea relies upon something far more subtle. Light. Photons possess no rest mass, yet they carry momentum. When light strikes a reflective surface, it exerts an extremely small force. On Earth, that force is negligible. Across the vacuum of space, acting continuously over months or years, it becomes surprisingly useful. Several spacecraft have already demonstrated solar sails. Large, lightweight reflective sheets slowly accelerate using sunlight alone. The acceleration is gentle. The fuel requirement is essentially zero. The concept changes again when sunlight is replaced by powerful lasers. Instead of carrying engines on board, an extremely light spacecraft could be pushed by concentrated beams generated far behind it. Several research programs have explored this possibility, particularly for tiny robotic probes weighing only a few grams. Such probes might eventually reach nearby stars within decades rather than millennia. Important uncertainties remain. Accelerating a microscopic spacecraft is one thing. Accelerating a vessel carrying people, ecosystems, and life support systems is something entirely different. Current proposals for crude laser-driven interstellar ships remain speculative. The underlying physics is sound. The engineering challenges are immense. A third possibility returns us to patience. If no practical propulsion system reaches another star within one lifetime, perhaps the lifetime itself is not the relevant unit. Generation ships embrace this perspective. Instead of racing across space, they accept the voyage as a permanent part of civilization. The ship becomes a world. Its inhabitants are born aboard. They live ordinary lives. Many never expect to see the destination. For them, the spacecraft is not transportation. It is home. Only distant descendants eventually arrive. This concept raises questions extending far beyond engineering. How large must such a society become to preserve sufficient genetic diversity? How should education be organized so critical knowledge survives for centuries? Would every generation continue supporting the original mission? History offers partial insights but no definitive answers. Human societies have preserved traditions over thousands of years. Religion, languages, and cultural practices sometimes endure across remarkable spans of time. Yet no civilization has ever attempted maintaining a single engineering project over centuries while isolated from every external community. Generation ships therefore remain scientifically conceivable but socially untested. The farther our thinking extends, the more another realization emerges. Distance is not the only obstacle. Energy is equally important. Accelerating a large spacecraft to a significant fraction of light speed requires extraordinary amounts of energy. Slowing down upon arrival requires just as much. Every proposed propulsion system ultimately confronts this fundamental accounting. Physics allows remarkable achievements. It demands that every joule be paid for. This brings us to a deeper perspective. Perhaps becoming an interstellar civilization is less about building one extraordinary spacecraft than about gradually transforming an entire civilization's relationship with energy. Throughout history, major advances have often followed access to greater energy resources. Fire, agriculture, coal, oil, electricity, nuclear power. Each expanded what civilization could accomplish. Interstellar travel may represent another step in that same long progression rather than an isolated technological miracle. There is another consequence of leaving the solar system that is easy to overlook. The farther humanity spreads among the stars, the less important any individual star becomes. Today the Sun supports essentially every known human activity. Tomorrow perhaps dozens of stars could do so. Eventually perhaps hundreds, or thousands. The death of one star would remain deeply significant for the communities living nearby. It would no longer threaten civilization as a whole. This is an extraordinary shift in perspective. The question changes from can humanity survive after the sun dies to something far larger. Can humanity become distributed widely enough that the death of any single star becomes only a local event? Astronomy offers an intriguing answer. Possibly, but only if suitable stars exist in sufficient numbers. Fortunately, the Milky Way contains hundreds of billions of them. Surprisingly, however, the stars that may offer the greatest long-term future are not stars like the Sun at all. They are far smaller, far dimmer, far longer-lived, and for much of astronomical history they received remarkably little attention. For most of human history, bright stars captured nearly all of our attention. The brilliant blue-white beacon of Sirius guided travellers across deserts and oceans. The reddish glow of Betelgeuse inspired myths and stories. Massive stars dominated constellations because they were easy to see even across enormous distances. Brightness naturally attracts curiosity, yet astronomy has repeatedly taught us that what appears most important is not always what is most significant. The same lesson applies to the future of life in the universe. Our own sun is often treated as the standard by which other stars are judged. It seems comfortably average. Neither exceptionally large nor unusually small. Neither especially hot nor especially cool. Because humanity evolved around a G-type star, it is tempting to assume that stars like the Sun must be the best homes for civilizations. Modern astronomy suggests otherwise. The Milky Way is not dominated by stars like the Sun. It is dominated by much smaller ones. These are the red dwarfs. A red dwarf is far less massive than the Sun. Its surface is cooler, giving it a reddish appearance. It shines much more faintly sometimes, producing less than 1% of the Sun's luminosity. From Earth, most red dwarfs are invisible to the naked eye. Not because they are rare, because they are dim. In fact, astronomers estimate that roughly 70% of all stars in the Milky Way are red dwarfs. The galaxy is filled with stars that ancient observers could not even see. This realization alone changes our perspective. The familiar night sky represents only a small fraction of the galaxy's true population. The universe is quieter than it first appears. Red dwarfs possess another remarkable characteristic. They're extraordinarily patient. Large stars burn through their hydrogen rapidly because their immense gravity compresses their cores to extreme temperatures. Fusion proceeds at tremendous rates, producing dazzling brightness but consuming fuel quickly. The Sun occupies a middle ground expected to remain on the main sequence for roughly 10 billion years. Red dwarfs behave differently. Because they are smaller, gravity compresses their interiors less strongly. Fusion proceeds much more slowly. Their lower luminosity reflects not weakness but efficiency. They consume their fuel with extraordinary restraint. Some of the smallest red dwarfs are expected to remain stable for trillions of years. Not billions, trillions. This number is difficult to appreciate. The universe itself is approximately 13.8 billion years old. No red dwarf has yet reached the end of its normal stellar lifetime. The cosmos simply has not existed long enough. Every red dwarf ever formed is still shining today. In an important sense, astronomers study their future through computer models rather than direct observation. The evidence supporting these models comes from well-tested stellar physics. The prediction extends beyond anything the universe has yet had time to demonstrate. That distinction is worth remembering. The extraordinary longevity of red dwarfs is strongly supported by theory. It cannot yet be confirmed through observation because the necessary time has not passed. Here another unexpected connection appears. Earlier we asked whether humanity might survive after the Sun dies. If civilizations eventually spread among many stars, the choice of destination becomes profoundly important. Settling around another Sun-like star merely postpones the problem. That star too will eventually become a red giant. Its planets will face similar challenges. A red dwarf offers something fundamentally different. Time. Not a little more time. Thousands of times more. A civilization established around a stable red dwarf might inhabit the same stellar system for periods exceeding the entire current age of the universe many times over. This possibility has transformed discussions about long-term habitability, yet it comes with complications. Life near a red dwarf would experience a very different environment from life on Earth. Because these stars emit much less light, planets must orbit much closer in order to receive enough warmth for liquid water. Instead of Earth's comfortable distance from the Sun, a habitable planet around a red dwarf may circle its star in only a few days or weeks. Such proximity introduces new effects. One is tidal locking. The same gravitational process that causes our moon always to present the same face toward Earth can also affect planets orbiting close to small stars. A tidally locked planet keeps one hemisphere facing permanently toward its star, while the opposite side remains in perpetual darkness. At first glance, such a world appears hostile, one side endlessly illuminated, the other endlessly night. For many years, astronomers assumed these planets would be unsuitable for life. More recent climate simulations have complicated that picture. If a planet possesses a sufficiently thick atmosphere, winds and ocean currents may transport heat efficiently between the two hemispheres. Rather than one side becoming unbearably hot and the other impossibly cold, large regions could maintain moderate temperatures. The evidence remains theoretical, but increasingly sophisticated. Computer models now explore atmospheric circulation under conditions unlike anything found in the solar system. Another challenge involves stellar activity. Young red dwarfs often produce powerful flares capable of releasing intense bursts of radiation. Some flare far more frequently than the modern Sun. Whether planetary atmospheres can withstand such activity over billions of years depends upon many factors. Magnetic fields, atmospheric composition, orbital distance, stellar age. Each system must be studied individually. Again, astronomy distinguishes carefully between evidence and uncertainty. Fact: many red dwarfs produce energetic flares. Evidence: several nearby rocky planets orbit within the habitable zones of red dwarfs. Hypothesis: some of these planets may remain habitable despite stellar activity. Unknown: how common long-term stable biospheres truly are around such stars. These distinctions matter because the search for life increasingly focuses on red dwarf systems. One particularly important discovery came with the identification of TRAPPIST-1. This small star hosts 7 known rocky planets, several of which orbit within or near its habitable zone. Their close spacing creates a compact planetary family, unlike anything in our own solar system. For astronomers, TRAPPIST-1 became more than an interesting discovery. It became a laboratory. Observatories began examining these worlds to determine whether their atmospheres survived what gases they contain and whether any conditions favourable to life might exist. The answers remain incomplete, yet every observation strengthens our understanding of how planetary systems differ across the galaxy. A broader pattern gradually emerges. Our solar system is not necessarily the template for all civilizations. Some may arise around stars much smaller than the Sun. Others may inhabit systems with several potentially habitable worlds, located close enough for relatively easy travel between them. Still others may develop beneath skies where the parent star appears larger but dimmer than our Sun. The diversity is astonishing. Perhaps the greatest surprise is philosophical rather than astronomical. Humanity often measures time using familiar references. A century, a millennium, even a billion years now seems almost comprehensible after following the Sun's evolution. Red dwarfs invite us to think on an entirely different scale. If intelligent civilizations endure around such stars, their histories might eventually span intervals so vast that our entire recorded past would resemble a single opening chapter. The rise and fall of nations, the building of pyramids, the first spacecraft, even the lifetime of the Sun itself. All could become early memories in civilizations still living beneath the quiet glow of stars that have scarcely begun their lives. This realization returns us to the documentary's central question from an unexpected direction. Perhaps surviving the death of the Sun is not primarily about escaping catastrophe. Perhaps it is about finding environments where time itself becomes abundant. And remarkably, modern astronomy has begun discovering more of these possible homes than ever before, using instruments capable of seeing worlds that earlier generations could scarcely have imagined. For most of human history, every discussion about life beyond Earth rested on a profound limitation. No one knew whether planets around other stars even existed. Ancient philosophers debated the possibility. Some argued that countless worlds must populate the universe. Others believed our solar system might be unique. The arguments were thoughtful, but they remained philosophical because there was almost no evidence to guide them. That changed only recently. In cosmic terms, humanity has entered the age of exoplanet discovery within the blink of an eye. Today, thousands of planets beyond the solar system are known. They orbit stars of nearly every size and temperature. Some are larger than Jupiter, others are smaller than Earth. A few circle 2 stars instead of 1. Some race around their parent stars in only a matter of hours, while others take decades to complete a single orbit. The diversity has exceeded almost every early expectation. Perhaps the most remarkable discovery is not any individual planet. It is that planets appear to be common. Before the 1990s, astronomers could only speculate about how frequently planetary systems formed. Now, the evidence suggests that planets accompany stars throughout the Milky Way. Our solar system is no longer an isolated example. It is one variation among an immense population. This realization quietly transformed one of humanity's oldest questions. Instead of asking, "Are there other worlds?" astronomers now ask, "What kinds of worlds are most common?" Finding these distant planets required remarkable ingenuity, because planets are extraordinarily difficult to observe directly. A star outshines its planets by enormous factors. Trying to photograph an Earth-like planet beside a Sun-like star is often compared to spotting a tiny firefly flying beside a powerful lighthouse from thousands of kilometers away. The glare overwhelms the target. Rather than looking for the planets themselves, astronomers learn to observe their effects. One of the most successful techniques is known as the transit method. If a planet's orbit happens to align with our line of sight, it passes across the face of its star, blocking a tiny fraction of the starlight. The change is almost imperceptible. For an Earth-sized planet crossing a Sun-like star, the brightness drops by less than 1/100th of 1%. Sensitive space telescopes can detect these minute variations with extraordinary precision. Each repeated dip becomes a clue. The interval between transits reveals the orbital period. The depth of the dimming indicates the planet's size. Multiple transits confirm that the signal is genuine rather than random noise. Another powerful approach measures the star itself. Although planets orbit stars, gravity works in both directions. A planet also pulls gently on its parent star. The effect is extremely small, yet modern instruments can detect the tiny back-and-forth motion produced as a star responds to its orbiting companions. This radial velocity method allows astronomers to estimate planetary masses. Together, these techniques provide a remarkably complete picture. Size, mass, orbital distance, sometimes even atmospheric composition. One mission proved especially transformative. Kepler Space Telescope spent years monitoring more than 100,000 stars, simultaneously patiently searching for the faint signatures of planetary transits. The mission revealed something astonishing. Small rocky planets are not unusual. Many stars possess planetary systems. Some contain multiple worlds orbiting in orderly arrangements. Others appear dynamically chaotic. No two systems are exactly alike. The galaxy is rich with possibilities. More recently, James Webb Space Telescope has extended this work in an entirely new direction. Rather than simply finding planets, it has begun examining the light passing through some of their atmospheres during transits. Certain molecules absorb specific wavelengths of light. By studying these absorption patterns, astronomers can infer the presence of substances such as water vapor, carbon dioxide, methane, and other atmospheric constituents. These observations remain challenging. Most involve large planets with thick atmospheres because their signals are easier to detect. Studying Earth-sized worlds remains much more difficult. Yet the progress is remarkable. Only a generation ago, detecting planets beyond the solar system seemed nearly impossible. Today, astronomers are beginning to analyze the chemistry of some distant atmospheres. Computer simulations have become equally important. Observations provide snapshots. Simulations explore evolution. Using the known laws of gravity thermodynamics, atmospheric physics and chemistry researchers model how planetary climates respond to changing stellar brightness, volcanic activity, atmospheric composition, and orbital variations. These virtual laboratories allow scientists to investigate questions that cannot be answered through direct observation alone. How does a planet recover after intense volcanic activity? How stable are atmospheres around active red dwarfs? How long can oceans survive as stars gradually brighten? The models do not replace evidence. They help interpret it. Every simulation must ultimately agree with observations or be revised. This relationship between measurement and modelling lies at the heart of modern astronomy. Each strengthens the other. Another major advance comes from studying planetary formation itself. Observatories such as Atacama Large millimeter-submillimeter array have imaged young stars surrounded by enormous disks of gas and dust. Within these swirling disks, planets begin taking shape. Dark gaps often appear where growing planets clear paths through the surrounding material. For the first time, astronomers are not merely reconstructing how planetary systems formed billions of years ago. They are watching similar processes unfold elsewhere in the galaxy. The evidence connects beautifully with our own history. The solar system was once such a disk. Earth itself emerged from countless collisions among dust grains, rocks, and embryonic planets. The story of our origins is no longer unique. It is part of an ongoing cosmic process repeated throughout the Milky Way. As these discoveries accumulate, another pattern emerges. Habitability appears less like a rare accident and more like a spectrum. Some worlds are clearly hostile. Others possess intriguing similarities to Earth. Many occupy uncertain territory between these extremes. The search, therefore, becomes increasingly subtle. Astronomers are no longer seeking perfect copies of Earth. They are trying to understand the many different ways a planet might remain stable enough for life. This shift has important consequences for humanity's future. If civilization eventually spreads beyond the solar system, it may not settle only Earth-like planets. It may adapt to a much wider variety of environments than earlier generations imagined. Technology could compensate for some limitations. Biology may adapt to others. The range of possible homes expands, yet caution remains essential. Even the most advanced telescopes cannot currently answer every question. A planet may appear promising while concealing hostile surface conditions. Atmospheric measurements often contain multiple possible interpretations. Clouds can obscure underlying chemistry. Unknown geological processes may shape climates in unexpected ways. Every discovery increases knowledge. It also reveals new uncertainties. That is perhaps the defining characteristic of modern astronomy. Each new instrument answers questions that previous generations considered impossible. At the same time, every answer opens entirely new fields of investigation. Today, scientists possess more information about distant worlds than ever before. And yet, some of the most important questions remain unanswered. How often does life actually emerge? How frequently does intelligence evolve? How many civilizations survive long enough to become interstellar? These questions stand just beyond the reach of current observations. The telescopes have shown us where to look. They have not yet told us what, if anything, is looking back. Modern astronomy has achieved something that would have seemed miraculous only a century ago. We can measure the chemical composition of stars hundreds of light years away. We can detect planets too small to see directly. We can model the evolution of galaxies across billions of years. We can reconstruct the history of the early universe from faint patterns in ancient light. Yet, despite these extraordinary achievements, some of the most important questions surrounding humanity's long-term future remain unanswered. This is not a weakness of science. It is one of its defining strengths. Science advances by identifying the boundary between what is known and what is not. Every new discovery sharpens that boundary rather than eliminating it. As we consider whether humanity could survive after the sun dies, we eventually arrive at questions that no telescope can yet resolve. The first concerns life itself. Earth provides exactly one confirmed example of biology. Everything we know about evolution, ecosystems, intelligence, and civilization comes from a single planet. This creates an unavoidable limitation. We do not yet know whether life emerges easily whenever conditions are favorable, or whether Earth represents an extraordinarily rare sequence of fortunate events. Both possibilities remain scientifically viable. Evidence strongly suggests that many rocky planets exist. Evidence also shows that water is widespread throughout the cosmos. Organic molecules have been detected in interstellar clouds, comets, meteorites, and protoplanetary disks. The basic ingredients of life appear to be common. The missing step lies between chemistry and biology. How often do simple molecules organize into self-replicating systems? No one knows. Even on Earth, where life is abundant, the precise origin of the first living cells remains one of science's great unsolved problems. Several promising hypotheses exist. None has yet been confirmed. If life itself remains uncertain, intelligence becomes even more mysterious. For most of Earth's history, life consisted entirely of microscopic organisms. Complex multicellular life appeared relatively late. Animals emerged later still. Technological civilization occupies only an extraordinarily brief moment near the end of Earth's long biological history. Does this pattern suggest that intelligence is rare, or simply that it requires patience? Again, the evidence remains incomplete. Earth cannot answer statistical questions by itself. One example is not enough. Another uncertainty involves longevity. Human civilization has existed for only a tiny fraction of the time available before Earth's distant future becomes inhospitable. Recorded history spans roughly 5,000 years. Radio communication little more than a century. Spaceflight only decades. Compared with 1 billion years that likely remain before solar brightening becomes a fundamental challenge, humanity has scarcely begun its story. This raises an intriguing question. Can technological civilizations remain stable over geological timescales? Astronomy offers no direct evidence. No confirmed extraterrestrial civilizations have yet been observed. Human history provides only limited guidance because our experience covers such a short interval. We therefore enter largely unexplored territory. Some researchers discuss this problem through the concept often called the longevity question. The issue is not whether civilizations can arise. It is whether they can endure. Natural disasters, environmental changes, resource limitations, technological risks, political instability, and unforeseen challenges all influence the long-term survival of intelligent societies. Astronomy identifies the available time. History reminds us that making use of that time is far from guaranteed. Another major uncertainty concerns biology beyond Earth. Human beings evolved under highly specific conditions. One atmosphere, one level of gravity, one magnetic field, one day-night cycle. How adaptable are we? Current evidence suggests considerable flexibility over short periods. Astronauts live successfully aboard space stations. Researchers spend months in Antarctica. Submariners inhabit enclosed environments beneath the oceans. People thrive from sea level to high mountain plateaus. Yet these examples all remain connected to Earth. Entirely independent civilizations living for thousands or millions of years in space present challenges unlike anything humanity has yet experienced. Will future humans remain biologically similar to us? Possibly. Will genetic engineering eventually allow adaptation to different gravitational environments? Perhaps. Would artificial intelligence become an increasingly important component of long-duration exploration? Quite possibly. Each of these possibilities rests upon technologies that already exist in early forms. Their long-term consequences remain deeply uncertain. Artificial intelligence introduces another fascinating unknown. Machines do not require oxygen in the way humans do. They tolerate radiation differently. They can remain inactive for long periods without aging biologically. Robotic explorers have already demonstrated extraordinary endurance. Several spacecraft launched decades ago continue returning valuable scientific data. Could future civilizations increasingly rely upon autonomous machines for exploration? Almost certainly. Could entirely machine-based civilizations eventually exist independently of biological life? Current science cannot answer that question. It belongs to the intersection of engineering philosophy and future technological development. The uncertainty lies not in whether advanced machines can be built. It lies in how intelligence itself should be defined. Then there is the question of communication. Suppose humanity eventually establishes settlements around several nearby stars. Even travelling at the speed of light, messages between them would require years. As distances increase, communication delays become decades, centuries, or longer. This transforms civilization itself. On Earth, governments, economies, and cultures depend upon relatively rapid exchange of information. Interstellar separation fundamentally changes that relationship. Each stellar community would gradually become more independent. Shared origins might remain. Shared daily experiences would not. Physics quietly shapes sociology. Perhaps the greatest uncertainty concerns consciousness across immense spans of time. Will descendants living billions of years in the future still think of themselves as human? Language evolves. Culture evolves. Technology evolves. Biology may evolve. The continuity connecting present humanity to such distant descendants could become increasingly difficult to recognize. Yet history again offers perspective. Modern humans remain connected to ancestors who lived tens of thousands of years ago, despite enormous cultural differences. Continuity need not require sameness. It may simply require an unbroken chain of inheritance. Astronomy contributes one further uncertainty: dark matter, dark energy. Together they appear to dominate the mass energy content of the universe, yet their true nature remains unknown. Fortunately, humanity's prospects for surviving the Sun do not currently depend upon solving these mysteries. Even so, they remind us how incomplete our understanding remains. The universe still contains fundamental ingredients that we cannot directly explain. Every prediction about the distant future therefore carries appropriate humility. The laws we know describe reality extraordinarily well. Reality itself may still contain surprises. This humility is not discouraging. It is liberating. Throughout history, many of the greatest discoveries emerged precisely because scientists acknowledged uncertainty, rather than pretending certainty existed. Questions drive exploration, not answers. As our journey approaches the frontier of current knowledge, one realization becomes increasingly clear. The greatest challenge is no longer calculating the Sun's future. That future is comparatively well understood. The real challenge lies in predicting ourselves. Stars follow the laws of physics with remarkable consistency. Civilizations follow far more complicated paths. Perhaps the ultimate mystery is not whether humanity can survive after the Sun dies. Perhaps it is whether humanity can remain curious, cooperative, and resilient long enough to make that distant future meaningful. Beyond that question lies the true frontier of modern astronomy, where observations grow sparse. Models become increasingly ambitious, and scientists work at the very edge of what evidence can presently support. Every scientific discipline has a frontier, not a physical boundary marked by signs or fences, but a shifting horizon where reliable knowledge gradually gives way to unanswered questions. For sailors centuries ago, the frontier lay beyond the edge of the maps. For geologists, it once lay beneath continents whose interiors could only be inferred. For biologists, it stretched into the microscopic world before the invention of powerful microscopes. For astronomy, the frontier often begins precisely where our instruments become just slightly less capable than our curiosity. This frontier is not a place of ignorance. It is a place of careful restraint. Modern astronomers spend much of their time distinguishing between what observations directly reveal and what must still be inferred. That distinction may appear subtle, but it is one of the reasons astronomy has become one of the most reliable sciences. Its greatest discoveries have usually emerged not from bold claims, but from patient measurements repeated until uncertainty steadily diminished. As we ask how long humanity could survive after the Sun dies, we eventually encounter questions that no observation can yet answer directly. The first limitation is time itself. Human beings naturally seek confirmation through observation. We trust what can be seen, measured, and repeated. Yet stellar evolution unfolds across billions of years. No astronomer has ever watched a sun-like star complete its entire life cycle. No telescope has monitored a planetary system from birth until its final stages. Instead, astronomers assemble the story much as a natural historian reconstructs the life of a forest. A single visit cannot reveal the entire process, but by studying countless forests at different ages, patterns emerge. Young saplings, mature woodlands, ancient stands, decaying ecosystems. Together they reveal the complete cycle. The same reasoning applies to stars. Throughout the Milky Way, astronomers observe stars at every major stage of evolution. Some have only recently ignited fusion. Others remain stable on the main sequence. Some have already become red giants. Others exist as white dwarfs, neutron stars, or black holes. Although no individual star has been observed throughout its entire lifetime, the galaxy itself provides billions of examples at different moments. This approach has proven extraordinarily successful. Its predictions repeatedly agree with observations. Even so, certain details remain uncertain. One example concerns the final fate of Earth. Earlier we explored the possibility that the expanding Sun may eventually engulf our planet. Here the evidence becomes more nuanced. As the Sun evolves into a red giant, it will lose a significant fraction of its mass through powerful stellar winds. Less mass means weaker gravity. Weaker gravity allows planetary orbits to expand gradually. Earth's orbit will drift outward. At the same time, tidal interactions between Earth's orbit and the Sun's expanding outer atmosphere may pull the planet inward. These competing effects produce one of the most fascinating unresolved questions in stellar evolution. Will Earth ultimately escape direct engulfment, or will it spiral into the Sun's outer layers? Current models differ in their details. Some predict survival as a scorched, airless world orbiting farther from a white dwarf. Others suggest complete destruction. Remarkably, this uncertainty has little effect on the broader conclusion. Long before either outcome occurs, Earth will have ceased to support complex life. Sometimes science can confidently answer the larger question while still refining smaller details. Another frontier involves planetary climates. Computer simulations have become extraordinarily sophisticated. Researchers now model atmospheric circulation, cloud formation, ocean currents, ice dynamics, volcanic activity, and interactions between planetary surfaces and stellar radiation. Yet every climate model necessarily simplifies reality. No simulation can include every grain of dust, every microscopic organism, every chemical reaction, or every geological process simultaneously. Instead, scientists compare many independent models. Agreement increases confidence. Disagreement highlights areas requiring further investigation. This continual refinement is a hallmark of scientific progress rather than a sign of failure. Exoplanets introduce another frontier. The most advanced telescopes can measure certain atmospheric gases on distant worlds. They cannot yet produce detailed maps of continents, forests, oceans, or cities. When astronomers describe a potentially habitable exoplanet, they are rarely claiming certainty about its surface. They're identifying promising conditions worthy of deeper investigation. Future observatories may transform this situation dramatically. Larger space telescopes now under discussion could directly image some nearby Earth-sized planets. Rather than measuring only bulk atmospheric properties, they might detect seasonal changes, cloud patterns, or perhaps even chemical signatures that vary over time. Such observations remain goals rather than current capabilities. The distinction matters. Science advances through achievable steps, not through assuming future success has already occurred. The search for life provides perhaps the clearest example of astronomy's frontier. Researchers increasingly discuss biosignatures. These are measurable features that may indicate biological activity. On Earth, oxygen exists in large quantities largely because photosynthetic organisms continually replenish it. Methane can also be produced biologically, though geological processes create it as well. Certain combinations of atmospheric gases may prove difficult to explain without ongoing biological activity. Yet even here, caution dominates scientific thinking. One gas alone rarely proves life. Multiple independent lines of evidence are required. Context matters. Planetary geology matters. Stellar radiation matters. Astronomers seek converging evidence rather than isolated clues. The same careful reasoning applies to technological civilizations. Occasionally researchers discuss technosignatures. Unlike biosignatures, which might indicate simple life, technosignatures would reflect technology itself. Examples include unusually regular radio transmissions, artificial illumination, industrial atmospheric pollutants, or large-scale engineering structures. At present, none has been confirmed. Searches continue. Silence, however, is not evidence of absence. It may simply reflect the immense difficulty of detecting civilizations separated by hundreds or thousands of light years. Perhaps they're rare. Perhaps they communicate differently. Perhaps they exist only briefly. Or perhaps our methods remain too limited. The frontier remains open. Another profound uncertainty concerns physics itself. The theories describing gravity, quantum mechanics, nuclear physics, and electromagnetism have passed extraordinarily demanding experimental tests, yet they remain incomplete. Gravity behaves differently from the quantum world. Dark matter has not been directly identified. Dark energy continues accelerating cosmic expansion for reasons still debated. These mysteries do not undermine our understanding of stellar evolution. The Sun will not suddenly ignore nuclear physics because dark matter remains mysterious. Nevertheless, they remind us that the universe still contains layers of reality beyond present understanding. Future discoveries may deepen rather than overturn today's knowledge. That possibility encourages humility. History repeatedly shows that every generation believes it stands near the end of discovery. Every generation eventually discovers how much remains unknown. Perhaps the greatest frontier, however, lies not in distant galaxies, but in prediction itself. Physics predicts the evolution of stars with remarkable precision. Predicting civilizations is another matter entirely. History is shaped by countless interacting decisions, inventions, accidents, and ideas. A single unexpected breakthrough can redirect centuries of development. A single unforeseen challenge can delay progress for generations. No equation can reliably forecast the path of intelligence across billions of years. This realization brings us full circle. The farther astronomy extends our vision, the more it teaches us the value of uncertainty. Not uncertainty born of confusion, uncertainty born of honesty. We know enough to understand that Earth is temporary. We know enough to predict the Sun's broad future. We know enough to identify promising worlds beyond our own. Yet we do not know what choices future civilizations will make with that knowledge. The edge of scientific understanding is therefore not a wall. It is an invitation. Every unanswered question points towards another observation, another mission, another telescope, another generation willing to look a little farther than the last. And as our exploration reaches this frontier, an even larger perspective begins to emerge. Perhaps surviving the death of the Sun is only one chapter in a much greater story about the future of the entire galaxy. Until now, our journey has revolved around a single star, its steady light, its gradual aging, its eventual transformation. From the perspective of everyday life, this feels like an enormous story. The Sun governs every familiar rhythm on Earth, from the changing seasons to the growth of forests. It seems natural to measure humanity's future against its remaining lifetime. Astronomy quietly asks us to widen the frame once more. The Sun is not the center of the universe. It is not even the center of our galaxy. It is one ordinary star orbiting through the outer regions of the Milky Way, completing a single revolution around the galactic center roughly every 230 million years. Since the dinosaurs disappeared, the solar system has completed only one orbit around the galaxy. During all of recorded human history, it has barely moved along that immense path. Our sense of permanence is once again challenged by cosmic time. The Milky Way itself contains somewhere between 100 and 400 billion stars. Many possess planets. Many are far older than the Sun. Some were already ancient before Earth had even formed. Others were born relatively recently and may continue shining long after our Sun has faded into a white dwarf. The galaxy is therefore not a collection of identical clocks. It is a vast community of stars, each existing at a different stage of life. This diversity changes the meaning of survival. If humanity eventually expands beyond the solar system, it will no longer depend upon the future of a single star. Instead, it will become part of the ongoing evolution of an entire galaxy. Imagine a civilization not in the sense of one government or one culture, but as a loose network of communities living around hundreds or thousands of different stars. Some settlements might orbit young yellow stars similar to the Sun. Others might circle ancient red dwarfs. Still others could exist within artificial habitats drifting between stars. At any given moment, individual systems would experience their own local histories. Some stars would be forming. Others would be reaching old age. A few would be ending their lives in spectacular explosions. From the perspective of the larger civilization, these events would resemble the changing seasons of an unimaginably vast landscape. The death of one star would be deeply important to those living nearby. It would no longer define the future of everyone. This idea introduces a profound shift. Human history has always been centralized. Every person who has ever lived has shared the same sky. Every civilization has depended upon the same planet. Even the first settlements beyond Earth will remain connected to the same sun. Only interstellar expansion truly changes that relationship. The center disappears. Instead of one home, there are many. Astronomers sometimes refer to this concept indirectly when discussing resilience. In ecology, systems with greater diversity often recover more successfully from disturbances. A forest containing many species is generally more resistant to disease than one dominated by a single tree. The same principle may apply on cosmic scales. A civilization distributed across many stellar systems is naturally less vulnerable than one concentrated around a single star. This conclusion does not depend upon speculative physics. It follows from simple geography. Distance creates independence. Independence creates resilience. Yet resilience is not immortality. The galaxy itself evolves. Stars continue forming because enormous clouds of gas still exist within the Milky Way. Over billions of years, however, those gas reservoirs gradually diminish. Each generation of stars locks away more material. Some of that material is later returned through stellar winds and supernova explosions, enriching future stars with heavier elements. The cycle continues, but not forever. Eventually, star formation throughout the galaxy will slow. The Milky Way of the distant future may become a quieter place populated mostly by older stars. This evolution unfolds on timescales vastly exceeding the Sun's remaining lifetime. Even so, it reminds us that galaxies like stars possess histories. They are not permanent structures. Another remarkable event also lies ahead. In about 4 to 5 billion years, the Andromeda Galaxy and the Milky Way are expected to begin a long gravitational encounter. The word collision can sound violent, but the reality is subtler. Galaxies consist mostly of empty space. Individual stars are separated by enormous distances. Direct stellar collisions are exceedingly unlikely. Instead, gravity gradually reshapes the overall structure. Spiral arms stretch and distort. Orbits change. Over billions of years, the two galaxies will merge into a single larger system. By remarkable coincidence, this galactic merger will begin at roughly the same time that the Sun approaches the end of its stable main sequence life. Whether humanity or its descendants still exist then is unknown. If they do, they may witness one of the grandest transformations visible anywhere in the nearby universe. The night sky itself would slowly change. New patterns of stars, brilliant tidal streams, the distant glow of merging galactic cores. The heavens would become dynamic in ways our present sky is not. This connection reminds us that the Sun's story unfolds within a much larger cosmic context. Its evolution is only one thread in an immense tapestry. Astronomers have also begun asking whether civilizations might eventually spread not merely across one galaxy but between galaxies. Here the evidence becomes much thinner. The distances separating galaxies are enormous. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. Even travel at a significant fraction of light speed would require journeys far longer than any discussed within our own galaxy. Physics does not forbid such voyages. Practicality remains another matter entirely. For now, intergalactic civilization belongs more to informed speculation than established science. The Milky Way alone offers enough opportunities to occupy countless generations of exploration. There is another implication that is easy to overlook. The heavier elements essential for rocky planets and life, carbon, oxygen, silicon, iron, calcium, phosphorus, and many others, were forged inside earlier generations of stars. Our bodies are composed of atoms created long before the Sun existed. Future stars will inherit material enriched by stars living today. In this sense, stellar death is not merely destruction, it is renewal. The end of one generation becomes the beginning of another. The same process that eventually ends the Sun's life has already given us every atom heavier than hydrogen and helium. We are participants in an ongoing cycle rather than observers standing outside it. This realization subtly transforms the original question. Perhaps survival should not be measured only by the continued existence of one planet or even one civilization. Perhaps it should also be understood as continuity within a universe that constantly reshapes itself. Nothing remains unchanged. Stars evolve, galaxies merge, atoms are recycled, life adapts, knowledge accumulates. The universe appears remarkably creative precisely because it never stands still. If humanity learns to participate in that larger rhythm rather than resisting it, then surviving the sun may represent only the beginning of a much longer journey. But even galaxies are not eternal. If we continue following time forward with the same patience that has guided us thus far, we eventually arrive at an even more distant future, one in which the sun has long since become a white dwarf, and humanity, if it still exists, must discover what it truly means to live after daylight itself has faded. At some point the sun will experience its final sunrise, not for Earth, because by then our planet will almost certainly have become an unrecognizable world long before. Rather, it will be the final sunrise for the sun itself, as a stable hydrogen-burning star. The transformation will not happen in a single moment. It will unfold across hundreds of millions of years, each stage flowing almost imperceptibly into the next. By the time the process is complete, the familiar yellow star that guided every chapter of human history will no longer exist. Yet the story will not end there. The sun's long life on the main sequence ends when the hydrogen at its center has been almost entirely consumed. Without fusion in the core, gravity gradually gains the upper hand. The core contracts. Its temperature rises. Hydrogen fusion continues in a shell surrounding the increasingly dense helium core. This additional energy pushes outward upon the sun's outer layers. The star expands. Its surface cools even as its total luminosity increases dramatically. The sun becomes a red giant. From a great distance, the change appears graceful. From within the solar system, it is transformative. Mercury disappears into the expanding atmosphere. Venus almost certainly follows. Whether Earth survives physically remains uncertain, but by then its surface has long ceased to resemble the blue world where life first flourished. The oceans have vanished. The atmosphere has been profoundly altered. Mountain ranges have weathered away and risen again countless times. Any traces of present-day civilization have disappeared beneath billions of years of geological change. If descendants of humanity still exist, they almost certainly no longer live here. The red giant phase is surprisingly brief compared with the sun's long main sequence lifetime. After exhausting helium within its core, the sun cannot continue fusing progressively heavier elements. Unlike much more massive stars, it lacks sufficient mass to ignite carbon fusion. Instead, it enters one final period of instability. Its outer layers begin drifting away into surrounding space. Gentle by astronomical standards, these stellar winds nevertheless carry enormous quantities of gas into the solar system. The material expands outward, illuminated by the intensely hot stellar core left behind. From afar, the result would be breathtaking. A glowing shell of gas, delicate and luminous, surrounding a brilliant central ember. Astronomers call this structure a planetary nebula. The name is somewhat misleading. Early observers thought these faint objects resemble planets through small telescopes. They have nothing to do with planets at all. They are the final visible farewell of ordinary stars. Planetary nebulae rank among the most beautiful structures in astronomy. Intricate filaments, expanding shells, soft blues, greens, reds and golds produced by glowing gases excited by ultraviolet radiation. Every one represents the ending of a star somewhat like our own. Across the galaxy, astronomers observe thousands of such objects. Each offers a glimpse of the distant future awaiting the sun. Eventually, even this beautiful stage fades. The expanding gases disperse into interstellar space. Only the stellar core remains. Compressed into a sphere roughly comparable in size to Earth, while containing about half the sun's original mass, the remnant becomes a white dwarf. Its density is extraordinary. A teaspoon of white dwarf material would weigh many tons under Earth's gravity, not because the atoms themselves become heavier, but because matter has been compressed to an astonishing degree. Electrons occupy states governed by quantum mechanics rather than ordinary chemistry. The physics becomes almost surreal, yet it is well understood. White dwarfs do not generate significant new energy through fusion. Instead, they simply radiate away the heat accumulated during their earlier lives. At first, they remain extremely hot. Over billions of years, they cool gradually. No white dwarf has yet cooled completely because the universe is not old enough. The oldest known white dwarfs still glow faintly. Far beyond the current age of the cosmos, they are expected to become black dwarfs. These hypothetical objects would emit almost no detectable light. The term hypothetical is important. The cooling process requires longer than the universe has existed. Therefore, no black dwarfs are believed to exist today. They remain predictions supported by well-established thermal physics. If humanity survives into the white dwarf era, daily life would look profoundly different from anything experienced today. The sun would appear as an intensely bright but very small point in the sky rather than a broad golden disk. Its warmth would be greatly diminished. The habitable zone that once migrated outward during the red giant phase would no longer exist in the familiar sense. Natural planetary environments suitable for surface life would become exceedingly rare within the old solar system. Civilizations would likely depend almost entirely upon artificial habitats or migration to other stars. This brings us back to one of the central themes running quietly through the documentary. By the time the sun becomes a white dwarf, the distinction between natural and artificial environments may have largely disappeared. Survival would depend not upon waiting for favorable planetary conditions, but upon deliberately creating them. Energy would remain available, not from the white dwarf alone whose luminosity steadily declines, but from many possible sources: nuclear fusion, stored fuels, gravitational energy, perhaps even technologies not yet invented but consistent with known physical laws. Importantly, none of these possibilities require overturning established science. They require engineering far beyond current capabilities, but engineering nevertheless. Some researchers have even considered whether planets orbiting white dwarfs might remain habitable under specific conditions. If a rocky planet migrated inward after the violent red giant phase, or formed through later processes, it might orbit close enough to receive moderate amounts of heat from the cooling remnant. Such scenarios remain subjects of ongoing investigation. Evidence is limited. Models continue improving. The idea illustrates how astronomy often reveals possibilities in places once considered impossible. Even the remnants of dead stars may host new chapters. Yet perhaps the most remarkable aspect of this distant future is psychological rather than physical. By then, if intelligent descendants still exist, the sun would no longer define their identity. It would occupy the place that ancient ancestral homelands occupy within human history today. A place of origin, a place remembered, a place honoured, not necessarily a place where anyone still lives. Civilizations change their centres over time. History repeatedly demonstrates this pattern. Cities rise, trade routes shift, capitals move, cultures spread across continents. The birthplace remains important without remaining central. The same may eventually become true on cosmic scales. Earth could become the archaeological birthplace of a civilization whose everyday existence unfolds light years away. The sun, once regarded as the source of all life, might become a cherished historical landmark rather than humanity's primary star. This possibility is deeply speculative because it concerns unimaginably distant descendants, yet it grows naturally from evidence already gathered throughout our journey. Stars evolve, planets change, habitable zones migrate, life adapts. Technology expands the environments in which intelligence can survive. Whether humanity accomplishes that transition remains unknown. Physics appears to allow it. History has not yet had time to answer. As we approach the end of this exploration, only one final step remains. We began by asking whether humanity could survive after the sun dies. Now, after following billions of years of stellar evolution, planetary change, technological possibility, and cosmic expansion, we are ready to return to that original question with eyes that have quietly learned to see the universe differently. At the beginning of this journey, we started with an idea that feels almost instinctive. When the sun dies, humanity dies with it. It is a simple thought, elegant, comforting in a curious way. If our fate is tied completely to the star that gave us life, then the story seems to possess a clear beginning and an equally clear ending. The universe, however, rarely follows the simplest narrative. Over the past billions of years, neither the sun nor Earth has remained unchanged. The continents beneath our feet have wandered across the planet. Entire oceans have opened and disappeared. Mountain ranges have risen only to be worn away again. Species that once dominated the Earth have vanished while entirely new forms of life have emerged in their place. The world we call permanent has always been quietly evolving. The sun has followed the same pattern. Its core has slowly transformed hydrogen into helium since before the first oceans formed. Its brightness has increased almost imperceptibly. Its future has been unfolding from the very moment nuclear fusion first ignited deep within its interior. Nothing about its evolution is sudden. Nothing about it is arbitrary. The same laws of physics that illuminated Earth's first dawn continue guiding its future today. One of the most remarkable discoveries in astronomy is that predictability does not diminish wonder. Knowing that the sun will become a red giant does not make the event less extraordinary. Knowing that stars are born inside vast molecular clouds does not make the night sky less beautiful. Understanding often deepens appreciation. Throughout this documentary, the original question gradually changed. At first we asked whether humanity could survive after the sun dies. Then we realized that Earth's habitability will end billions of years before the sun itself reaches its final stages. The challenge shifted from surviving stellar death to surviving stellar aging. Later another transformation occurred. We stopped thinking about Earth as the only possible home. The solar system became a collection of potential destinations rather than a single planetary system. Mars, the icy moons of Jupiter, Titan, artificial habitats. Each represented a different answer to the same underlying problem. Eventually even the solar system proved too small. The stars themselves entered the story. Red dwarfs revealed lifetimes measured not in billions but in trillions of years. Exoplanets demonstrated that worlds are common throughout the galaxy. Interstellar travel, once dismissed as pure fantasy, became an engineering question rather than a violation of physics. Each new perspective widened the horizon. The sun became one star among many. Earth became one world among countless others. Humanity became one possible civilization within an immense cosmic landscape. Perhaps the greatest change, however, occurred in the meaning of home. At the beginning of the story, home seemed inseparable from place. A particular planet, a familiar sky. One atmosphere, one ocean, one sunrise. Astronomy gently challenged that assumption. Life has always depended less on location than on conditions. Liquid water, available energy, stable chemistry, protection from excessive radiation. Those conditions can exist in different forms across different environments. Technology expands that range still further. If future generations create habitats capable of sustaining forests beneath artificial skies, or establish thriving settlements around distant stars, then home may gradually become something that is built rather than inherited. Human history already hints at this transformation. Our earliest ancestors lived in small regions of Africa. Over tens of thousands of years they crossed deserts, mountains, forests, islands and oceans. Each migration required adaptation. Each new landscape gradually became home. No single migration erased the memory of earlier ones. Instead, humanity carried its history forward while continually expanding its definition of belonging. Perhaps the same process awaits on cosmic scales. The first lunar settlement would not erase Earth. The first Martian city would not replace the Moon. The first interstellar colony would not diminish the solar system. Each new step would simply enlarge the circle within which humanity recognizes itself. There is another lesson hidden within stellar evolution. Every atom of carbon in our bodies was forged inside stars that lived and died before the sun was born. The calcium in our bones, the oxygen we breathe, the iron in our blood, all were created in ancient stellar interiors and dispersed across the galaxy long before Earth existed. In a very real sense, humanity has already survived many stellar deaths. Not biologically, chemically. Without those earlier generations of stars, rocky planets could not have formed. Life as we know it would never have emerged. The ending of one star became the beginning of another. The universe has always recycled its past into its future. This realization gives the original question an unexpected depth. The death of the sun is not an isolated tragedy. It is part of a continuous cosmic process that has been unfolding for billions of years. Stars illuminate planets. Stars manufacture heavy elements. Stars disperse those elements into space. New stars form. New planets emerge. Perhaps new life begins again. The cycle continues. Whether humanity remains part of that cycle depends not upon astronomy alone, but upon choices made across countless future generations. Science can estimate the available time. It cannot determine how that time will be used. Perhaps civilization expands patiently into the solar system. Perhaps it eventually reaches neighboring stars. Perhaps descendants of humanity live beneath the dim glow of ancient red dwarfs trillions of years from now. Or perhaps our story follows a very different path. The evidence cannot yet distinguish among these possibilities, and that uncertainty is entirely appropriate. The future has not happened yet. Astronomy is remarkable precisely because it allows us to see both certainty and mystery at the same time. We know with extraordinary confidence that the sun will not shine forever. We know with similar confidence that the universe contains countless other stars. Between those two facts stretches a vast landscape of possibility. As our journey draws toward its quiet conclusion, the original belief has changed almost without our noticing. Humanity's future is not automatically bound to the lifetime of the sun. Neither is survival guaranteed. The universe offers neither promise nor prohibition. It offers opportunity. Whether that opportunity is realized remains one of the greatest unanswered stories in existence. And perhaps that is the most hopeful conclusion science can honestly provide. Not certainty. Time, an extraordinary amount of time. Enough for countless discoveries. Enough for countless mistakes. Enough for civilizations to rise, adapt, and perhaps one day carry the memory of one small yellow star, far beyond the place where its light first gave them life. The night sky has always invited two very different responses. One is to measure, to calculate distances, temperatures, masses, and ages with increasing precision. To build larger telescopes, develop more sensitive instruments, and gradually replace mystery with understanding. The other is simply to look upward in quiet reflection. Neither response is complete without the other. Throughout this journey, we have followed the evidence as faithfully as modern astronomy allows. We have watched an ordinary star reveal itself as a living system governed by nuclear fusion and gravity. We have seen Earth transformed from a permanent home into one chapter within a much longer cosmic story. We have travelled outward through the solar system across the galaxy and into futures measured not in centuries but in billions and even trillions of years. Yet despite all that distance, we have repeatedly returned to something deeply familiar, the search for home. Perhaps that is why the future of the sun feels so personal. The sun is not simply another star in an astronomical catalogue. Every memory of daylight, every changing season, every forest, every ocean current, every breath taken by every living creature has unfolded beneath its light. Even the oldest rocks on Earth bear the imprint of energy that began in the sun's core long before those rocks existed. To understand the sun is in a quiet sense to understand the conditions that allowed us to ask questions at all, and yet the universe gently reminds us that permanence has never been one of its promises. Stars are born, stars evolve, stars fade, galaxies slowly change their shapes. New planetary systems emerge from the remnants of older ones. The cosmos does not preserve individual objects forever. Instead, it preserves possibility. That perspective changes the meaning of endings. When viewed through the span of a human lifetime, the eventual death of the sun feels unimaginably distant. When viewed through the history of the universe, it becomes one event among countless others that have unfolded across billions of years. Long before our sun existed, earlier generations of stars lived out their own lives. They forged the elements that would one day become mountains, oceans, trees, and living cells. Their endings made our beginning possible. In that sense, the future awaiting the sun is not unusual. It is participation in a story far older than the solar system itself. There is something quietly comforting in that realization. The universe is not standing still while we struggle to keep pace. Everything is moving together. Every planet, every star, every galaxy, even time itself carries every structure forward through an ongoing process of change. Humanity happens to exist during one remarkably peaceful chapter of that process. A stable yellow star, a temperate rocky planet, an atmosphere rich in oxygen, conditions gentle enough for curiosity to flourish. Whether those conditions remain forever is almost beside the point. They've already lasted long enough to produce minds capable of wondering what comes next. Perhaps that is one of evolution's most extraordinary achievements. Not merely intelligence, perspective, For the first time in Earth's history, one species can look billions of years into both the past and the future, using nothing more than observation mathematics and patient reasoning. No previous generation could have known that the sun has a finite lifetime. No previous civilization could have searched for planets around distant stars. No previous age could have recognized that the Milky Way itself is only one galaxy among hundreds of billions. Knowledge has quietly expanded the size of humanity's home long before any spacecraft could. Whether our descendants eventually settle other worlds or remain forever within the solar system is something astronomy cannot yet answer. The evidence leaves both possibilities open. What it does tell us is that the universe appears neither especially hostile nor especially welcoming. It is simply governed by consistent laws. Those laws have already carried matter from the hearts of ancient stars into living cells on Earth. They may yet carry conscious life much farther, or they may not. Science is at its most honest when it accepts that some questions remain unfinished. Perhaps that unfinished quality is what makes the future so compelling. If every answer were already known, exploration would lose its purpose. Instead, each discovery opens another horizon. Each telescope reveals another layer. Each generation inherits questions larger than those left by the one before it. The sun will continue rising over Earth for countless generations beyond our own. Long after today's cities have become part of history, its light will still cross the 8-minute journey through space to reach this small blue planet. For us, that is more than enough time. For the universe, it is only a brief moment. And somewhere within that immense span between human memory and cosmic time rests the question with which we quietly began. If one ordinary species born around one ordinary star learns to carry its knowledge beyond the place where it first opened its eyes, then when the sun finally grows dark, billions of years from now, will that moment be remembered as the end of humanity's story, or simply as the last sunset seen from the world where it first began,